The fact that you and I had to retire and change that, like, unironically, I was like, what are you doing? I literally checked the version history to see you change it. I was like, SDR does the same thing. I read our version as
Hello. Hello. All right. Good morning. Welcome to the Aerospace Engineering Senior Design Symposium. My name is Dr. Felix Owera, and I instruct this class. I want to welcome you, especially parents that are here. I think you should all be very proud. These kids have done a lot, and you're going to see that this today. Enjoy the symposium. This morning we're going to have presentations. These presentations will be what we call rapid fire, 12 minutes. There'll be no questions. But essentially we have judges that are looking at these presentations, and they're going to be seeing this as a pitch to help select the winners eventually. In the afternoon, we'll move over to EB3. We'll have lunch, and then at 1:30, we'll start with the second half of this, which is the poster and video symposium, as it were. Teams will have their prototypes, they'll have their posters, and it's an avenue then to ask questions, to know a lot about what they're doing. And I promise you, they know a whole lot about their project now, so you're going to hear a lot of exciting things in the afternoon. So we're going to kick off with the AIAA DBF team. And then we'll have our fixed wing section go first. We'll have the space section go second. And then we'll have a multi-rotor section third. Please speak into the microphone so that the people watching this online can hear you. But also, after your presentation, please just move over here so that you can have a group photo with Riley while the other teams set up. So thank you all for coming, and I hope you have a great time. DBF, let's go.
So you guys can pass this microphone, and then whoever talks the most can kind of just stand in front of this microphone and we'll pick up too. Good morning, everybody. My name is Joseph Deneke. I'm the graduate TA for the fixed wing section. I'd like to introduce AIAA DBF. The team leader is Galen Day. They're going to a competition this coming weekend in Tucson to fly their aircraft. And so yeah, I'll hand it over to them for the presentation.
Hello, everyone. As Joseph said, we are NC State's team for the 2024-25 AIAA DBF competition. Our senior design team name was chosen as Randy Whitson's farewell tour. rip to a king. And we are presenting today on our aircraft, the Highway to Howl, and its autonomous glider, the Thunderwolf. This is who we are. I'm Galen Day. I'm the project manager, propulsion lead. We have Landon Hyatt off to my right, structures lead. Graham Atherton to my left, our payload lead. Preston Duffy's our CAD and Sim lead. Kira Shook is our manufacturing lead. Luke Mayo's stability and controls, and Jake Russell is our aerodynamics lead and also our pilot. The purpose of the project this year, the whole rule set was defined around a mock-up of the X-1 test flights back in the late 1940s. Basically a supersonic test flight program. The X-1 was carried inside of the B-29, kind of nested inside its modified bomb bay, released, and then achieved supersonic flight, rocket-powered although. So this year we mocked that by having some external fuel storage tanks in the form of commercially available beverage bottles. And we also have an autonomous glider we have to deploy.
Yeah, so our goals for this project is to successfully complete 4 missions. The first mission is to stably fly our aircraft. It'll just be clean, no payload. For mission 2, we'll add our pylons, which will have about 9 pounds of like a mix of rust and steel in them. And then for mission 3, we'll deploy a glider and get it successfully to land with inside about 200 by 200 foot box. And then for ground mission, we have to load our aircraft as fast as possible. And here's our concept of operations. This depicts our mission 3, where we'll take off, climb, and enter stable flight, and we'll drop our glider, which will hit a 180-degree turn, land, and then we'll land our aircraft, gain full points. And then here is a rendered model of our aircraft. You can see we have a high wing H-tail configuration with a tricycle landing gear. We have about a 6-foot wingspan, which was about the max we were allowed, and we have twin booms connecting our tail to our wing.
Okay, so for the pylon design solution, we decided to go with a multi-piece pylon with rails attached to them to improve our ground mission time. These pylons will be about 4 inches long, so that way we have good enough clearance for our wings for better aerodynamic performance. And we also made them about 2 inches wide, 1 inch long as well for strapping onto the pylon. And like Preston was previously saying, we're going to have steel and a rust mixture to improve our weight.
All right, for our glider itself, we opted to go with the flying wing design. We are limited to about 0.55 pounds, so by eliminating a tail section, we can get down to only 2 servos, which are able to work elevons, which are able to control both the roll and the pitch, and fully control the glider all the way down to descent.
Okay, so for the glider activation, because it needs to activate autonomously, we decided to use a magnetic sensor called a reed switch. Whenever that sensor sends a signal, we have a Lewis script that basically activates post-deployment, which will have elevon deflection and LED light, which you can see in the screen down there. And we also have servo rods to hook through the glider for deployment and carriage flight.
All right, for the fuselage of the aircraft, we decided to go with a square-bodied fiberglass composite layup reinforced by an aluminum truss structure. This is mainly to counteract the buckling intrinsic to the fiberglass, in addition to an aluminum motor mount at the front of the fuselage.
All right, here you can see our overall functional block diagram for our aircraft and its subsystems as a whole. Of note, you can see that attached to our receiver is a 6-axis gyro. While our aircraft does have designed passive stability, the gyro acts to provide active stability as well, which greatly improves handling and ease of piloting, as well as it works to decouple all 3 rotation axes. And then for the glider itself, you can see that it has its own flight control computer, which is able to work for autonomous flight, and you can see the reed switch and the GPS as well that Graham mentioned before.
For our manufacturing, so one of the main components that we did was water jetting a lot of our parts. So we water jet our truss that goes inside the fiberglass fuselage that Landon was talking about. And then our front landing gear was also water jet out of aluminum stock and then welded into a T-bracket that was then wrapped with a carbon fiber layup for stability. And then in that middle picture at the bottom, you can see that's our motor mount, which was water jet cutted and then bent into shape to put inside the fuselage. So the next big component that we used for our aircraft was a composite layup. So we first used a wire cutter, hot foam wire cutter, to cut out the airfoil shape of the wing that we would then wrap in a carbon fiber layup. And you can see in that picture that it's red. So we added a red like powder dye that would just give it an aesthetic. And you can see a couple of our different layups and with the vacuum bag as well.
All right, for the glider itself, we decided to 3D print it so that we could get the exact shape that we desired. You can see a little bit of our iterative process here, although we have moved on significantly further since this picture. You can see before when it was orange, we were using PLA, but that's a bit too brittle. So towards the end, we switched to a nylon carbon fiber reinforced 3D printer filament, which allows us to drop multiple times without it basically exploding upon hitting the ground.
Right, here you can see some of our structural analysis. In the top right, there's the design topology optimization used to but to dictate the design solution for the truss, in addition to the nominal deformation and stress that are most concerning in the aircraft, but have been verified and are safe structurally.
Okay, here, do you mind hitting me again? So this video shows a slow-mo of our glider activation VVNT. There's a stopwatch to the top, which you can't really see that well, but essentially what I'm doing is I'm timing how long it takes for the LED to deactivate post-deployment to verify that we are getting good LED activation.
So another one of the validation and verification tests we conducted was a tough test. Thank you to Joseph for letting us use the gust generator over at MEE West. But this is a flow visualization technique which allows us to find the stall angle of our aircraft. So as you can see, as we pitch the aircraft's nose up into the flow, you can see the tufts on the upper surface of the wing start to depart that clean, smooth surface of the upper wing, and that shows when the flow is separated from the wing and gives us our stall angle. So that's from that angle gauge on the top of the fuselage there. Then another test that we conducted using the gust generator was our glider separation test. So after we confirmed that our glider was able to activate upon release, we needed to determine where in flight we should be able to separate this glider during our flight mission. So we moved through a bunch of different angles of attack and side slip angles to develop a deployment envelope, which lets us know where the pilot should be releasing the glider in flight. So here's some of our flight test videos. This is mission 1. This is clean. This is no payload. This is over at HMAC, which is a local Academy of Model Aeronautics airfield that we've been flight testing at. They've been great, been super helpful for us, but the plane flies great. It's really smooth. Like Luke was talking about, that gyro really helps with some rate stabilization stuff. So it deals with wind great. It flies beautifully. So. And then here's mission 2. This is about 9 pounds of payload on the wings right now. As you can see, it handles it fine. It's definitely a little fast on landing, but it handles it very great. So.
Okay, and for our final mission, we did a glider deployment. If you see there, it deployed upside down, but then it auto-stabilized, and it started banking towards the waypoint that we had. We released it a little too early, so we weren't able to get full activation on the waypoint, but it was setting its heading towards the waypoint that I set in my script.
This is our schedule. We are very near completion. As you can see, the finish line is only a few days away. We leave for our competition, as Joseph mentioned, on Wednesday, about like 2 in the morning, so that's fun. And speaking of competition, so far we are #1 in the world at this moment. That was the proposal. That was back in October. We get our design report score tomorrow. I wish we had it for today, but we get it tomorrow, and then we will fly, and then I believe a week after competition, we get our final results. We like to do some acknowledgments. Harnett Mini Aero Club has been incredibly helpful. A bunch of old guys down near Dunn flying planes and then giving us lots of advice and letting us fly planes with them. Dr. Edwards has been super helpful. He's given us lots of good advice, been a good faculty advisor for us. Dr. Aware as well, running senior design and supporting us the whole way. Future Dr. Denecki has been incredible, given us an amazing amount of feedback, really helped our report scores. Finally, we'd like to thank the other senior design teams, ULFR, Greenwing, and Lufka, for creating a bartering system and letting us make a new tail when we didn't have enough materials to. And here's a hype picture that we took last night when the NCSU men's baseball won, and that's the only thing we've shown to other DBF teams. So We're hoping to be a little mysterious and take home first place when we come back. Thank you, everyone.
It does, yeah, it does. So you can pass this one around, and then if you want to talk, if you're talking the most,
So I'll probably use this one, and then these guys will pass.
yeah. So the next team that I'll be introducing is Team Greenwing, and the team lead is Matthew Knight.
Good morning, everybody. Thank you all for being here today. We're very excited to show you guys what we've been working on for the past 10 months or so here. So here's our agenda for today. So like Joseph mentioned, my name's Matthew Knight. I'm the project manager for this team. I'm joined by Elko, who is our propulsion lead, Evie, who is our CAD/simulation lead, Jimmy, who is our stability and controls lead, Lizzie, who is our structures lead, and Aiden, who is our aero lead. So our mission that we're focusing on with this aircraft is bringing value to the Southwest Climate Hub. This Climate Hub is responsible for over half of the total crop value produced in the United States. That's mainly due to longer growing seasons, more sunshine, but the big issue with this area is high drought losses. These losses right now are deductible as ordinary business losses, and so these types of technologies like drought management, precision irrigation, they're in use, but they're not used very often because it's easier to just write off the losses. So what we're trying to do is to make these methods more profitable for the producer, and we're doing this through a fixed wing UAS that is used in a service-based approach. So that service-based approach looks like this. The customer gets recommended for a survey by these government agencies. They reserve a survey date with us. We deploy our aircraft and conduct survey with multispectral and LiDAR sensors, and then we contract out our post-processing and analysis to a subcontractor, and that goes to results in a mobile app. So this is our ConOps. You can see we're launched from a mobile ground control station, something like a small utility van, and then on the first flight over a field, we would discretize the survey site into a set number of cells, a grid, and then on the subsequent flights after that, we do about 6 to 10% of the cells on each flyover. And so we collect data, get as much data as possible, and then offload that to a post-processing contractor and publish recommendations.
So you can see here that we have our conceptual development objectives. So when the project was assigned, we essentially had to develop something that had STOL capabilities, was rapidly deployed, and flew within a 400-foot ceiling. So from there, that formed our performance and mission system objectives. And then from those, we actually defined functional and design requirements. So then with these requirements in mind, we had these conceptual design candidates. You can see the two that are boxed in red. Those were the ones that we went with. Initially, we had the one up top there. You can see that all of these designs are able to use a pusher propeller configuration, which was important for our mission systems, our scanners. Initially, we went with the twin boom V-tail, but realized that was not going to be compatible with the necessary propeller. So we decided to go with the bottom right, which is a tailless canard, which is rather unique.
Okay, I'm going to talk a little bit more about our design process. So after the initial sizing that Jimmy just mentioned, we basically split into the different subsystems that we had and did a series of trade studies. We did a first round of them, and then we changed the weighting and made sure that we arrived at the same conclusion again, and then we ended with our baseline design, which would be the next slide. So here's our design. Like was mentioned before, it is a pusher canard configuration. And on the, no, it's on the left. No, it's on the right. On the right is the sensor turret, which it completes our mission through 360-degree rotation through the 2 dual servos. You can see the shafts the rotating shafts are in red. This mounts onto the underbelly of the fuselage in the front, and it has interchangeable sensor packages. The ones that are currently in the render are the ones that we proposed for our ConOps to Blue Skies. It's a multispectral and an FPV camera.
This diagram here shows our electronic subsystems in the plane. So pretty much everything runs through our QPilot Orange flight controller. We have our control surfaces, our control surface servos down on the bottom, our power system, and then a bunch of peripherals like FPV cameras and our GPS module.
Yeah, and then so before we moved into manufacturing, we wanted to prove the feasibility of our design. So each sub-team broke apart, and we did some computational work. You can see some examples of that. For aerodynamics, CFD was used for stability. AVL for propulsion was done computation, like mathematically through MATLAB, and then structures was done with SolidWorks.
So once the spring semester started, we really started diving into the manufacturing of our inside aircraft. And so as you can see here on this slide, we mainly utilized CNC hot wire foam cutting, 3D printing, additive manufacturing, and laser cutting to get most of our designs. And this was really, really fun, very, very challenging, and we definitely learned a lot through this. So as you can see here, we listed some of the challenges that we saw doing the manufacturing this spring. And there's, of course, different categories as you see here, but some of the biggest ones included our planned shipping times and just the logistics of getting the parts in, getting them scheduled, and keeping a good timeline when the semester is pretty dense. And so we had a good time. We learned a lot, and we know for next time we should definitely plan time and a half of what we think we're going to need for putting together parts. And so, but it turned out really good.
Okay, so next we did a series of verification and validation testings, and these were just to ensure that each of our subsystems met the design requirements that we had outlined. So from here we did around 2 to 3 tests for each of our subsystems, and you can see that these are listed on the slide right here along with some of the pictures of the test.
So highlighting a couple of these tests, the first one you see on the left is the gust generator stall test, as DBF already kind of laid out how that goes, but essentially we take one of our wing sections to the gust generator at West Annex. We applied tufts to the top and an angle sensor to the side, and then with 2 people we can adjust the angle of the wing in the stream of air, and we can watch those tufts on the top. And they should be laying flat under normal conditions, but at a certain angle we'll start to see them lift and start acting erratically, and that's how we know the air is separated, indicating a stall, and we can record the angle with the sensor on the side.
One of the other ones that we wanted to highlight was obviously we 3D printed a couple of really important parts on the aircraft, so we wanted to ensure that the 3D print quality met the design requirements. So how we tested that is we printed test coupons according to ASTM D638 geometry. And then, so the top one is they were printed vertically on the bed, and then the bottom stress strain curve is horizontally on the bed. From there, we just derived the material properties and then compared them to our FEA results from earlier, and basically successfully concluded that the margin of safety is good on all of our 3D printed parts.
So as you can see here, this is our finished prototype. We put this together about 2 weeks ago before the initial fly day. Some really cool things that we got to add towards the end of the semester were canard winglets, which definitely helped our stability. Some might say it was a little too stable, as you'll see in just a second. But it really helped our stability. We have our vertical tails. We ultra-coated all the surfaces. We 3D printed the motor mount, the radome, and hot wire cut all the airfoils. And so it came out looking really clean, really nice, and we were really happy with it. And so on our initial flight testing, we ended up not being able to roll on takeoff at Mid-Pines, as we've all been warned
throughout the year, there was a lot of wind. And with the pusher canard configuration, we had to do a ground launch since the propeller would be coming from over your head if you were to hand launch it. And so due to safety concerns, we did a ground launch. The ground was a little bit bumpy, and because of that, our front landing gear ended up taking some damage on takeoff. After that, we ended up switching up some things, and it mitigated some of these contributing factors here, such as the rear landing gear placement, just to balance out the moments about the CG, flap effects, insufficient elevator size, and so forth.
Yeah, so in the week following that first attempt, we made some changes. I'll highlight a couple of them. As Elko mentioned, we moved the rear landing gear forward to help that nose come up a little bit easier, as well as made the whole canard, and by extension the elevators, a little bit larger, 2 inches in span total. But then the big one that I want to point out is that first one. We took almost 5 pounds of weight out of the aircraft. That was mostly out of the fuselage. We had realized it was a little over-engineered, and even with all the weight taken out, it was still plenty strong. We took out some of the unnecessary systems like the GPS and the nose wheel steering. We found that it didn't work that great. It broke pretty quickly. So we just took that out, and ultimately these changes led to a test that you will see on the next slide.
So then came Judgment Day V2 on March 28th. Matt went full power and released the brakes. You can see a nice smooth takeoff even for a canard aircraft. In order to avoid the trees, Matt is going to bank left. That reduces our vertical lift, but you can see really good aileron control. And we would totally show you our buttery smooth landing, but in the interest of this 12-minute presentation, I'm going to skip the next slide. And so you can see that when it did climb, it exhibited great static stability and, aerodynamic qualities. It didn't stall. You can see that it was kind of, floating in the vertical axis, and that's because we are pushing the limit of wing loading. So the wings were kind of on the verge of being able to provide the correct amount of lift. But overall, we were super happy with how it performed. And upon the landing, we suffered some minor damage to the front landing gear and the canard.
So looking at next steps, if we were to continue building this aircraft and developing it further, we're still in the concept demonstration phase right now. So we would do more vehicle prototypes and more flight evaluations. Following that, we would move on to mission systems demonstration, and then after that, low rate production and deployment by 2035, which was our goal with the NASA Blue Skies competition that we were a part of. So in conclusion, we're very happy with our results. We successfully proved a very unique configuration that fit our design requirements. We used a lot of 3D printed parts, 15.5 pounds of filament total, and that allowed us to pretty much produce almost everything ourselves for the airframe. The big thing we learned is that failure is pretty much mandatory. We failed in total 3 times before we took off. With faux fly, we built a half-scale aircraft, and then at Mid-Pines, that's 3 total times failing to take off. But that taught us a lot. And another thing I want to highlight is the abuse loads. This is mainly for structures. The critical load in a lot of cases that caused stuff to break was not the aerodynamic loads or anything of that sort. It was just taking it in and out of the lab, bumping it into stuff. So we're glad that we considered that, because things could have been a lot worse if it was more fragile. But yeah, we were happy with the result. Thank you all for listening to our presentation. Thank you to DBF and ULFR as well for providing us with some of the parts we needed at a critical time. And yeah, thank you.
I didn't realize that.
Start with the conclusion. Sorry.
You three go. Yeah, we got it.
So next up, I'd like to introduce Team Flying Farmers, led by team lead Carson Roby.
Good morning, everybody, and thank you for coming. And now I'm going to hand the mic to Ethan to start the presentation.
All right, good morning. We are Team Flying Farmers, and our project title is SCYTHE, which stands for Survey and Control Yield Through Targeted Herbicide Emission. Here's our presentation outline. I'll just be going over the process our team took during senior design for both last semester and this semester. Here's the personnel. I'm Ethan Twitty, the payload and avionics lead. Carson is our project manager. Owen is stability and control lead. Finn is structures lead. Andrew is propulsion lead, and Peyton Worst is the aerodynamics lead. Here's our organizational structure, which our team followed, which basically just depicts how the team interacted with each other and how we communicated to important project customers and faculty advisors here at NC State. Here's the project timeline. It was broken down into 3 different phases. Phase 1 and 2 were completed in the fall semester, which were really focusing on the design of our aircraft. And phase 3 was manufacturing and testing, which we've been doing this spring. So our purpose was really to develop a UAV which can quickly identify common weeds in tobacco fields and eradicate them by deploying herbicide. We identified a need for a rapid integrated approach for targeted weed removal within the agricultural industry. So our mission statement was to provide farmers with a tool which could reliably both locate the weeds and deliver herbicide to get rid of them. And here's some of our objectives. Really for senior design, we focused on levels 1 and 2, and level 3 would be what we would focus on if we had a larger budget and timeline.
So looking into our project goals, the main objective of SCYTHE is really to target those weeds that were left behind in the initial crop dusting phase. And this ultimately reduces the effort that the farmer has to interact with after the crop dusting phase, so they don't have to go out and find all the weeds. And so not only are we able to identify these weeds, but we are able to quickly deliver the herbicide to them. And this ultimately leads us to a 2-in-1 solution to a common problem. Here's our concept of operations. It's really a 2-cycle process where we initially assemble the plane. It's hand launched into ascent, where we then do cycles of loops that are in certain patterns for our photogrammetry. We then descend, charge our plane while we do post-processing for photogrammetry. We then do the process over again, where instead of surveying, this time we are deploying the herbicide to the allotted areas. This is our functional block diagram. It's just how the individual subsystems of SCYTHE communicate with one another.
So now talking about the actual design solution of SCYTHE. So as seen in the 3D render, it just shows some prominent features such as the twin boom tail, the dual motor configuration, as well as the rectangular wing. And then it's accompanied by a table which shows key dimensions and what we originally designed for them to be, and then what they actually ended up being after manufacturing. And as you can see, they're all relatively similar. And an important design criteria we had to meet was SCYTHE had to fit within a 5-foot by 3-foot by 2-foot box. So that kind of inspired a sense of modularity when designing SCYTHE. So as seen in this picture, when disassembled, it fits within the box. And also another important design criteria is fitting all of the avionics as well as the payload within the fuselage. So as seen in this render, all of the avionics and payload fit within that. And then also a render of our motor and propeller configuration. And then here are just some notable dimensions, such as our 1-foot chord, 8-foot wingspan, and about tip to tail length of 70 inches.
So during the preliminary phase of design, there were a few key decisions that we made that stuck with us. We wanted an H-tail from the beginning because for such a lightweight aircraft, stability was a bit of a concern. So we wanted 2 vertical tails and a very wide horizontal tail, and the twin boom H-tail allowed us to support that. And then as a result of that, we wanted twin motors to take advantage of the structures that were already in place for the booms. We wanted an 8-foot wingspan because we wanted to push our weight as much as was allowed, which was a 20-pound weight limit. And we, based on some hand calculations, we figured an 8-foot wingspan would be what was necessary to generate the amount of lift for that weight. And we settled on a hollow fiberglass fuselage to allow for the maximum amount of internal volume to accommodate our tank for the herbicide. Then here are some important design features just based on that preliminary phase. Most importantly, an endurance of about 12 minutes, range of about 14 kilometers, thrust to weight of about 1.4, and a cruising speed of around 40 miles an hour. And then moving into the critical phase of design, we started using more advanced tools to make sure that our design would function. We used computational fluid dynamics to make sure, to validate that the aerodynamics were as expected from our hand calculations, make sure it would perform. And we used finite element analysis on all our structural components to make sure that they would hold up to the loading that they were expected to experience. And then as we began manufacturing and ordering parts, we made some key changes. Initially, we had one single larger wing spar that went through the entire wing, but we instead swapped that for 2 smaller wing spars, and we increased the diameter of our booms so that our spars could slot through our booms instead of having to bolt them together, just to reduce the complexity. We added a dedicated structure protruding from the forward section of the wing in order to make it easier to attach our fuselage. We modified our wing joint to accommodate the new internal structures. We reduced the empennage complexity to reduce the weight because our CG was a concern at the time. And we changed the internal configuration of the avionics to allow for more space for the tank, and we redesigned our landing gear to be stronger.
So after we had started building our prototype, we designed a series of tests to ensure that each subsystem of Scythe was performing as required, and that Scythe would be able to fulfill or execute the mission that it was designed for. The table on the right or on the left there shows the comprehensive lists of all the tests that were run along with what each individual test was looking for. We employed both simulational and experimental methods to test each of the subsystems. In general, the main things that we were looking for was the stall condition of Scythe to make sure that it was actually able to take off at low velocities since it had to be hand launched. We were testing the structures to make sure that none of the main structural systems would fail with the wing loading and upon landing. We were testing the propulsion system to make sure it would give us enough thrust to take off quickly and to make sure that the batteries were enough that would have the endurance necessary to fly the entire mission. And also testing to make sure that the combined avionics system would operate without any anomalies. So here are listed a few of the main tests that we were running. The first one was the weight and balance test. Here we were looking for the location of the center of gravity on Scythe. And this is very important to make sure that, for the stability purposes, to make sure that it's able to trim properly. And the second test that is listed is the payload deployment, making sure that upon activation of the controller that our herbicide is actually able to deploy and to deploy enough. The next thing we were testing for was the deflection of each control surface to make sure it gives us enough authority over all of our degrees of freedom. And on the right is our Tufts test, where we put a segment of our wing in front of a wind wall, and we were looking at what angle of attack it begins to stall in which there is flow separation. And then here is our final prototype of Scythe as fully constructed. The second picture shows Scythe to scale, and the picture on the right shows the final layout of the avionics inside of the fuselage.
So 2 Fridays ago, on the 28th, we had our first test flight. Before the flight, we had 2 of our teammates assemble Scythe. It took about 25 minutes. Once we were done assembling, we took it over to the launch area. where we made sure the camera was recording and activated all the avionics. For our takeoff, we had Owen hand launch it into the air, which was successful. And because Scythe has a thrust weight of almost 1.5, pretty much any takeoff angle would have been successful. Once we got into the air, we did multiple loops around the field to prove that the camera could capture accurate and precise images. We did multiple low passes to deploy the herbicide to prove that we could deploy over specific areas to kill any weeds necessary. And then once we were done with the deployment, we came in for a landing. On Mid-Pines, we had a dirt road that we had to land on, and we did have some issues with the front landing gear due to some rocks, but other than that, it was a smooth landing. Once we were landed, we were able to extract all the avionics and calculate some data based off of the camera and the internal GPS. On the right, you can see the photogrammetry that was stitched together from over 1,500 photos captured by the camera. And we were also able to calculate a total flight time of around 8 minutes from the remaining voltage on the batteries. So the benefit to customer is a keen farm analysis, accurate multiple species weed identification, and herbicide spraying. And all of our parts were affordably priced and commercially available. So in case a local farmer needed to replace anything, they could go to their local Lowe's or Amazon and order the parts there. All of our deliverables would be practical for any farmers that needed to use it. We were able to show that we could deliver on the fully stitched together photogrammetry 3D model, as well as deploy herbicides in the correct environment. And because Scythe was manufactured to be assembled in a small amount of time, most of our parts were easily swappable, which meant any farmer could upgrade for quality or higher performance in the future. In conclusion, and in the future design, Scythe's mission was successfully tested and flight proven on the flight day. This was after multiple failed attempts at faux fly, which we learned and improved upon. All of our original customer requirements, minus a few, were met and exceeded. This is due to us over-designing in the beginning to ensure that even through issues we could outperform and complete our mission. We did face some manufacturing challenges with composite manufacturing and 3D printed PLA parts, but in the end we were able to complete our mission and create a successful product. And on flight day, we were able to have a stable and very controllable flight and complete our dual mission, which we had to push into one overall mission due to flight constraints. But other than that, we had a completely successful mission. Thank you for your time.
So for all of our guests out here today, the parents especially, the remaining 3 teams for the fixed wing section designed and flew VTOL aircraft, which essentially means that they can take off vertically and then transition into a conventional type of flight. So I'd like to introduce the first of those 3 teams, ULFR, which is led by team lead Hannah Nguyen.
Thank you, Joseph. Good morning, everyone. We are Team ULFR, Unmanned Laser Farming and Reconnaissance. This is our team. I'm Hannah Nguyen, Noah Troxler, Caleb Goebel, Chris Basili, Sasha Patel, and Ainsley Lundquist. So in our research to identify current agricultural challenges, we talked to actual farmers. In this picture, it shows half the amount of weeds that were hand-picked on a 13-acre farm. So you can see there's a large opportunity for technological improvement here. So we made it our mission to develop a novel fixed-wing solution that will modernize weed removal by 2035. In our system, we will be sustainably powered, have remote ID, be capable of having a diverse payload and sensor system, have versatile flight modes, and be modular.
So how do we plan to accomplish all of these goals? Looking at our concept of operations, you'll see we plan to vertically take off from anywhere in a farm. Then at a high altitude, we'll transition into forward flight and begin phase 1 of our mission, where we will capture a lot of information about the field below using our image payload. Then we'll land, swap out our batteries, and swap in the laser payload, and go back out and hover at a very low controlled altitude. In this phase, we will precisely eliminate the weeds. So, we know what you're thinking, a laser on an aerial platform, right? What the heck's going on there? Well, there's actually ground-based platforms that do this, such as Carbon Robotics. They basically take a big machine, bunch of lasers, and drive it back and down the field. So, the reason this technology is so effective is that the two most common types of chlorophyll found in weeds and crops, chlorophyll A and B, see high percentage of light absorbance along the blue wavelength light spectrum from 440 to 450 nanometers. Additionally, unlike herbicides, with a laser solution, weeds are unable to adapt, so they can't build up like, herbicide dependencies where problems just start cascading. Regenerated cellulose actually has a higher percentage absorbance than regular cellulose. So how would we target a laser, right? It's got to be pretty precise. There's got to be something that we'd be doing to make sure it's safe. We determined the best solution for our system would be synthetic aperture radar in a full-scale model. More commonly known as SAR, this technology allows for a ton of information to be collected. It's currently used on satellites, but with current advances in the field with things like a nanosar that bring the weight down a lot, we do expect it to be feasible by 2035 as stated in our mission statement. And in a full-scale model, we would use machine learning algorithm to kind of back out the data from SAR, such as crop differentiation, using things like backscatter coefficients to actually feed into the laser payload for its targeting system. So looking at a bit more of a technical sense of our plane, our functional block diagram, you can see, as Hannah mentioned earlier, we are fully sustainably powered with lithium-ion batteries and a solar array on our wings. And that feeds power into our flight controller, which then distributes power and commands to the rest of our components.
All right, so we can now take a closer look at some of the critical parameters associated with our design solution. Namely, you can see that our endurance was a pretty important factor for this. So for forward flight, it was calculated to be 20 minutes, and for hover, it was calculated to be around 5 minutes. In addition to this, you can also see that our final weight for our design solution was 18.49 pounds. And this was important as one of the design requirements was that our UAV could not exceed 20 pounds. In addition, you can see our final length of 5 feet, final span of 8 feet, and final height of 2 feet also fit our design requirements for this project. So we could also take a look at our CAD, our completed CAD for a design solution. Starting with our exploded view, you can clearly see all the important parameters and components of our plane. You can see our 4-motor configuration, our motor spars, our wings, and our wooden fuselage assembly. We can also look at the tilt rotor assembly, which was the mechanism attached to our front motor spars that allowed for our UAV to be able to transition between those hover and forward flight modes. You can also see our wing spar connection, which was utilized to enhance the structural integrity of our wings. So determining the feasibility of our design solution was a critical component of the engineering design process. As you can see, ANSYS was utilized for both CFD and structural simulations, and AVO was utilized to help calculate our static and dynamic stability derivatives. Before moving on to any other components of the design process, we made sure that all feasibility tests were passed.
All right, so now we can take a look at how the UAV was actually manufactured. First, we want to go over some design choices and changes that we made to help in the manufacturing process. One of these things that we want to highlight are the finger joints along the wall of the fuselage, which you can see in the top picture there. These basically allowed for a strong and easy connection point between the walls of the fuselage, allowing them to be slotted together like puzzle pieces, making it easy to put them together and have a lot of surface area for glue to bond to. We also want to point out the slot for the horizontal tail at the back there. That allows for an easy and strong connection point for the horizontal tail and allows us to quickly mount it at the angle that we need. Next, we want to point out the horizontal tail itself. This was changed from a thin tapered shape to a thicker rectangular shape, which had the dual benefit of being easier to manufacture and more structurally secure. So now moving into some of the big components of the UAV. First, we want to look at the fuselage. This all started at the laser cut. The walls of the fuselage were laser cut out of plywood, and then these were glued together and allowed to cure in front and rear sections. Then these front and rear sections were attached together using more wood glue and a carbon fiber spar that runs through the middle. Next, we're going to look at the wing manufacturing. This was done by hot wire cutting insulation foam around a laser cut airfoil stencil. This provided foam cores that you can see on the top right there. This was then wrapped in a carbon fiber epoxy composite, which provided a smooth and strong skin. And then both halves of the wing were attached together with an interior carbon fiber spar. Finally, we want to go over some of the 3D printed components of our UAV. These are pretty much all of them. You can see the flight controller mounting plate, the laser gimbal assembly, the tilt rotor gearbox, and the motor mounts, which are currently shown in their curing phase. It's important to note that the infill for each of these components was carefully selected based off of the anticipated loads. So for example, the gears in the gearbox and the motor mounts were printed at 100% infill due to the strong loads that they would endure during flight.
Thanks, Noah. So we put this UAV through an extensive battery of tests. We want to make sure that the UAV is ready for our flight day. Now, just taking a look at some of the ones that we have pictured here, we have our hover test, our control surfaces test, our static thrust test, as well as our thermal test. Now, taking a closer look at some of these tests, specifically the aerodynamics and structures tests. For the aerodynamics test, the first test we see here on the top left is the full CFD test, where we put the UAV through a variety of pitch, yaw, and roll scenarios in order to determine its aerodynamic characteristics. Another test we did for aerodynamics is the gust generator stall test, where we attached tufts to the top surface of the wing and held it in front of a gust generator to determine how stall propagates across the wing and at what angle of attack that stall propagates. For structures tests, we see the wing deflection test, where we flip the UAV upside down and put sandbags in order to determine the wing deflection. Another test that we did is the motor spar loading test, where we hung weights upside down from the motor mounts in order to simulate the force that we would get from the motor and propeller. Now, some more tests we did were the communication range and hover tests. We found it was really important during some early fall testing to test our full communication range for safety purposes. We did this using a line of sight test as well as a wooded and interference test. Our final test we did was a hover test. This was a huge test that incorporated all the subsystems of the plane and was simulating our low altitude flight conditions. Now, taking a look at some of the modifications that we made after our testing, based on our wing deflection test, we were seeing too much deflection, and so we added these aluminum wing struts, which helped us transfer load into the fuselage and decrease some of that deflection at the wingtips. Another change that we made was to the motor spar and motor mounts. These were really thin, and so we were seeing vibrations from the motor forces, and so making them larger helped with that. You can see here we have our final prototype. You can see our four motor configuration, carbon fiber wings with a foam empennage. You can see our payload up at the front with our laser, and on the right wing you can see our solar panels.
So next up we have a clip of our flight test. We're in hover mode right now, and you can see us start the transition here, we move down, and then we are fully transitioned here. The instability that you see here is because this was our very first flight, so we hadn't been able to adjust our controls for it. Additionally, that day it was really, really windy. But despite that, we were able to have a successful flight and landing. These are pictures from our flight test. In the top left, you can see that we are setting up our plane, which involves putting on the wings and propellers. Bottom left is our plane in hover mode. Top right is our plane in cruise flight. And then here is the budget for this project. You can see that propulsion was by far and away the most expensive, and that is because of our 4-motor configuration.
Okay, so wrapping up here with a little bit of what do we provide to a customer. So with a laser-based solution, we do eliminate that dependency on herbicides or spraying any harmful chemicals, which provides safety to our end users. Additionally, being VTOL capable and multi-role platform, we allow farmers to have more of a versatile end user experience where they can kind of customize their missions to suit their needs, and they can gain some efficiency boosts by using that data captured in our first phase with the camera to kind of do things like field planning, crop rotation mapping, and a lot of other different benefits. Additionally, with that solar panel and LiPo batteries and the laser eliminating the herbicide usage, we are an environmentally sustainable solution that promotes eco-friendly farming practices. So before we wrapped up, we want to give a huge thanks to our TA, Joseph. We would have not been able to do this without his help. I'm sorry for asking you so many questions. We also want to thank all of the professors that helped us, the farmers that we talked to at the beginning of this project, Dr. Aware, the other senior design teams, and all of our fellow classmates that helped us along the way. If you want to check out our full flight test video, feel free to scan the QR code or come see us at the poster session. Thank you, guys.
If you're talking here, make sure you're kind of close to it. Okay. So Caleb was kind of back and you can hear it very well.
I think Mason and I are going to just kind of split the podium because he's going to start off.
I'll just give him well, you guys can use this mic and then you can pass this one around to people who are talking. You can use both of these microphones.
Okay. Which one do you want me to use? Doesn't matter. Use them. I'll use this one. Let's be serious here.
So the next team I'd like to introduce is Team Lufka, and it is headed by Derek Geiger.
Good morning, everybody. Thanks for coming. I'm going to pass this over to Mason to kick this off.
All right, so we are Team Lufka. Good morning, everybody. This is our comprehensive presentation. So our team, starting with Derek Geiger as the project manager, we had Aiden Kibler as our communication and structures lead, we had Jonathan Baxter as our systems and avionics engineer, Logan Hale as the flight testing and propulsion lead. I was in charge of stability and control and manufacturing, and Steven Stuntz as our finance and aerodynamics lead.
All right, so getting into the presentation outline, today we're going to go over our project description, ConOps and functional block diagram, our design solution in our CAD, manufacturing, and then we'll get into testing, talk about our flight, our results, and get into conclusions and remarks. And then I'll read out the purpose and mission statement for this project. So the purpose of this project is to design and manufacture an unmanned aerial system capable of performing everyday tasks related to the monitoring and management of livestock. And then our mission statement is to collaborate as a cohesive team in the design, construction, and testing of a UAS that can replace manual tasks in livestock identification, management, and health monitoring while enhancing efficiency and promoting ethical practices.
So the need for this project is there's a few current concerns. First of which is that cattle farming is a growing industry as populations rise, and conversely, the agricultural workforce is decreasing. There's new challenges related to the efficient care and management of livestock, and there's some concerns with current ID methods such as branding causing discomfort to animals. And there's a need for smarter, more efficient methods of carrying out everyday tasks on farms. So we have four main objectives for our project. The first of which is to design, build, and test an unmanned aerial system. The second of which is to implement a high-definition RGB camera on that aerial system, and that will be used for livestock monitoring. And then the third mission is to implement an infrared camera on the aircraft. And then the fourth mission is to optimize the UAS assembly and payload integration time.
So if we kind of take all that and distill it down into an image here, we created our ConOps diagram. So you can see on the left, basically our mission is to take off vertically and then cruise out to a remote monitoring site where our UAS will then collect data on a herd of cattle through multispectral data analysis, and then send that data back to a ground station. And then once the mission is completed, it'll head back and vertically land back where it took off from.
So here's our functional block diagram. It's basically a diagram of our entire aircraft and the ground station. We have the two lithium-ion batteries that power the entire aircraft, and the flight controller that controls all of the control surfaces, the rudder, elevator, and aileron, and the 5 motors.
So now we're going to go on to our design solution. Here's our system level CAD model here. The total weight was estimated to be around 17 pounds. The longitudinal CG was about 25 inches after the nose, which is about 5 inches after the leading edge of the wing. And the total span of the UAS longitudinally was around 64 inches, while the wingspan is around 8 feet. So here's an exploded view of our UAS. Here you can see a lot of the internal structural components as well as some of the avionics. Something important to note is that the entire skeleton of our UAS is essentially all carbon fiber spars, which makes this a very strong design. And now I'm going to talk about some of the redesigns that we made for manufacturing. For the fuselage and the wing box, initially in the CDR design, we had an ABS or 3D printed wing box mounted to a balsa wood fuselage. Ultimately, this was not going to be structurally stable and it was very expensive and hard to replace. Instead, we redesigned this to be a PVC wing box with a foam fuselage design. Next is the empennage spar placement. So here, initially we had the spar going from the tail all the way to the fuselage, about 6 inches into the fuselage. This was ultimately going to be too longitudinally stable, or our pitching stiffness was going to be very high, making it very hard to maneuver the plane. Instead, we decided to feed this all the way through to the front of our fuselage. This was going to push our tail 28 inches forward, which ultimately fixed this problem and made it a lot more maneuverable. And this also increased our structural stability. Now we're going to go into some of our manufacturing. First, we're going to go over the final manufacturer prototype, and then we're going to go into some of the components or subsystems. First off, here is the final manufactured prototype. So we're pretty proud of the fact that this looks pretty much exactly like our CAD design. And here we're going to go over our wings, VTOL prop system, and the tail system manufacturing.
So to start off with the wings, very similarly to other groups, we designed our wings with a foam core and then did a carbon fiber wrap over it to add some stiffness and I guess strength for impact damage. One of the biggest concerns for us is we had a lot of hardware mounted on our wings, so we had to work our carbon fiber layup around that, which we'll kind of get into later. And I guess one of the VTOL or the components that is mounted to the wing is the VTOL prop system. That is mounted through a aluminum extrusion, as you can see in the image on the bottom left, where we essentially took a carbon fiber spar and routed it through that aluminum, which is tied into the wing, and then epoxied it in place to create a rigid mounting point for our VTOL system. And looking at our tail is probably the most complex part that we had to manufacture out of carbon fiber, specifically because of the horizontal part, the horizontal tail. That is done all combined with the red empennage system you can see in the bottom. So that kind of gave us some special considerations for carbon fiber manufacturing there. So kind of condensing all that into the challenges, we had a lot of issues with our hardware mounted on our wings, as you can see in the top two images. On the left, you can see that when we were wrapping our carbon fiber over the wing, we couldn't quite get it to align with, or our hole to align with the VTOL mount, so we had to kind of fiddle with it a bit, and it kind of pulled the carbon fiber out. And in doing that, we shifted the fabric a little bit. So you can see on the right, we lost a little bit of fabric coverage over the root of our wing, which left some exposed foam. But through structural testing, we were able to determine that it is fine. It didn't really impact anything at all. And then at the bottom, you can see when we were manufacturing our horizontal tail, we had to include the empennage mount inside of it because it is directly attached. So in order to risk, that would risk puncturing the vacuum bag. So we had to add some fabric in there to keep it from ripping our bag. But it all turned out okay in the end.
So this is an overview of our verification and test plan. This is every single test listed up here on the board. We have them split by subsystems to try and evaluate the efficacy of every single component we manufactured and how they work before we actually go up in the air. And for today, you can see the two in red are what we're mainly going to cover. They're probably our most key tests that we performed, and in interest of time, that's what we'll be looking at. For our hover test, the objective is essentially, we are a VTOL aircraft. The objective is essentially to ensure that we can hover stably as well as climb vertically for our takeoff. And we needed an open space. You can see the video on the right. We're doing pretty well. It actually drifts a little bit. It was a pretty windy day, and we were pretty happy with the fact that we stood roughly still, or we could stay roughly over the same area with the ground. And we rated this as evidence of steady hover as well as a stable climb.
So next is going to be the CG determination test. As most of you guys know, the center of gravity of a UAS is very important for any aircraft. this becomes even more important when we add a vertical option to the UAS. So to make sure that our center of gravity is exactly where we wanted, I decided to go a little bit more complex and use the parallel lift method, which essentially uses 4 cables that suspend the UAS over the ground, as you can see in the test setup here. And to be able to measure the force, I use the hook scale, and then I use these force values or tension values to do a moment balance and get the results that you can see in the table on the bottom. And you can see this is very consistent test with under 1% error for pretty much every trial.
We began on flight day with our pre-flight checklist and our final Ironbird test. We began our vertical takeoff and we climbed to about 50 feet above ground level. And then once we were there, we began our transition by engaging our forward-mounted prop. We began to translate successfully and we had achieved stable flight, but we underestimated the amount of distance we were going to need to transition. So if during that transition phase, we were stable in flight, but we underestimated how far we were going to need. So it led to us coming into some obstacles a little early with a hill and a wooded area. So when we got close to this, we had a sharp pull-up maneuver that we didn't have the airspeed for, which then prevented us from being able to bank away from that tree. So looking at the post-flight results, we had some serious damage to our airframe, but thankfully there was no serious damage to the wings and tail composites. The wing box suffered some damage, so we used PVC concrete to chemically bond that back together. But with the little damage there was to the wing and tail, it was very easy to attach those back onto the fuselage, which led to us having a total repair cost of $0, which we were really happy about. So in conclusion, we went over our project overview. We looked at the CAD design and the manufacturing challenges that we face. We talked about our 2 most critical verification tests and the overview of our flight day and our repairs. This concludes our presentation. Thank you. Appreciate it. Thank you, Joseph.
Back to my 24 on our slide, so if we can change that real quick. Okay. We're stuck in the past. Appreciate it.
So, stand, talk into the microphone, very close, have the mic up here, and then when you're talking to this one, be close to it as well.
Do you guys want to do the name thing? Or do we
if you're standing, if you're using this, have it
just
close
me
to
do
you.
it? Alright,
So the final fixed-wing team that I'd like to introduce is Team Aero Havoc with their Rampart aircraft, and the team lead is Andrew Bauer.
All right, first of all, thank you all for coming out. I believe we are the last fixed-wing team, so congratulations to the previous 5, but we are Team Aero Havoc, and today I would like to talk to you about our aircraft, what we call the Rampart, or codenamed Agent P. So before we get started, just a little bit of a presentation outline. I'm going to first start off with just our team personnel overall, and then get into actually our project overall, our project goals. And then much like these other teams, going to go into manufacturing, some of our verification, validation, and testing, and then ultimately show you some of our flight test videos, which are pretty funny, and then ultimately ended up with some conclusions of this project in general. So with that being said, my name is Andrew Bauer. I'm the project manager. I'm joined by Caleb Case. He is our systems engineer. Daryl Harp, our manufacturing lead. Robert, our avionics and financial lead. Deanna Patel, our communication liaison, and then Cameron Williams, our test and safety lead. So with that being said, much like the previous 4 groups, we were tasked with designing a fixed-wing aviation solution for agriculture. I will not lie to you, I think us as a team, we kind of struggled to come up with an idea that would actually benefit from being a fixed-wing design and be something more than just a quote-unquote camera on a plane for the sake of completing this project. So with that, we were actually able to identify a need, and the need that we focused on was on crop damage, specifically that caused by large pests, quote unquote, or agricultural nuisance wildlife. So you can see here pictured is an example of how feral hogs and large pests will actually damage and cause over billions of dollars to crops in the United States alone. So our goal was to develop a system that could actively assist farmers in addressing these damages and help them out in the long run. So that led into our actual ConOps. So we pictured our solution as a VTOL-capable aircraft for remote launching and landing of the aircraft, and they would fly around for a significant amount of time, really taking benefit of that fixed-wing design over some of the multi-copters that you'll see later, use that longer range, longer endurance, and sort of act as an aerial scarecrow, quote unquote. So with that being said, I'll lead it over to Daryl Harp.
Yes. So right now I'm about to go over the functional block diagram. Similar to the previous groups that have been up here, pretty much it just serves as a complete framework to see how our plane is completely designed. And we decided to put up both our prototype and a long-term vision. The only two differences that you can note between the prototype and the long-term vision is the inclusion of the surrounding systems. We decided to add that since we wanted to relay communication to an outward source, such as with NOAA, since that's the main framework of our project. And we also added a bit more connections to the long-term vision to make it more refined. Slide, please. And for the design process, we decided to do like a top-down approach. So rather than just trying to focus on the aircraft itself, we decided to do the payload first and work our way out. It makes more sense to do this manufacturing-wise since it's a bit easier to do, since you know exactly what the payload is, so you're able to accommodate the aircraft and make it like that. Slide, please. And to continue on the design process, design alternatives examples, pretty much we had a tilt rotor design, and pretty much the motors just tilt up and down to get it from VTOL to STOL capabilities. And we wanted to make sure that we were confident in making that decision, so we decided to make a pros and cons list. And we pretty much compared it to other modern forms of flight, such as with STOL and dual mode. And this pretty much showed us and gave us the confidence that our design would actually work. Slide, please. And to further refine and boost our confidence in this system, we decided to do a sensitivity analysis. And pretty much there are a bunch of selection criteria that we put throughout our designs, and they each got a weighted score. Then with this weighted score, which is based on our personal judgment of how much it contributes or is beneficial to our design, we decided to give it a number. Then for this example that you can see on the board, this is for our takeoff and landing, and pretty much we compared the VTOL to the STOL method and the dual mode. Then pretty much once you summed up all the weighted numbers, you got 3 numbers at the bottom, and it pretty much tells you which of these 3 are the best for our situation. Slide, please. And just as a broader scope, we did a sensitivity analysis on a lot of the aircraft components because we felt like this is a very confident way in order for us to decide, okay, what parts should go on here, what parts shouldn't, what other considerations should we have for this.
And that leads us to our design solution. So we knew we needed to focus on speed and maneuverability so we could deploy at any farm, anywhere. And that led us to the VTOL tilt rotor remote takeoff and landing solution. And we also knew our design needed to be compact so that we could assemble it on site if need be. Next slide. And we also knew that because this is a prototype, we figured we were going to crash at some point. So we made sure we had extreme structural integrity. We actually did crash in our first flight and had to do minimal repairs due to this. And then we also, because we are VTOL, we had to have a high thrust to weight ratio so that we could take off during hover.
So going into the manufacturing of Rampart itself, we generally broke this down into 3 subcomponents, starting with the lifting surfaces, fuselage, and electronic bay. So mostly for the lifting surfaces, as all the other teams have done before us, we started with cutting out foam sections, which afterwards we used a manual hot wire to cut out and trace our desired airfoil shape, after which we did a composite layer up onto it for structural rigidity, and then ultra-coated it for just cosmetic purposes. Moving on to the fuselage, this is composed of a 3-pin inner shell, which is then wrapped in foam and ultra-coat. This was not a key structural component of the overall frame, but does provide housing bay for all the electronics. And then some structural components that really make up the rigidity of Agent P is the carbon fiber spar inside the main wing and the 2 fiberglass tail booms. All of this is connected into one armature. It provided more than enough structural stability even during our crashes. This was the one part that never really broke during all our testing and maneuvers. So going to the next slide, this is the most complex part of our overall design, which is our tilt rotor system. This consisted of 2 servos and 2 protruding carbon fiber spars from the leading edge, which is then our motors are connected to. This provided a challenge just because of all the fastener challenges that we ran into, like how do we get the servo connected to the protruding bars, how do we get the motors connected to the servos. But overall, at the end, we made something quite rigid, and we were pretty confident that it was going to work out. In the end, our overall weight, next slide please. Overall weight of Agent P turned out to be 19.6 pounds with a thrust to weight ratio of 1 in forward flight and 1.5 in VTOL and 6-foot wingspan.
All right, so as we manufactured different parts of Rampart, we conducted a series of tests to validate the performance and design of our subsystems. With our wing structure, we applied both the 3G and negative 2G loading by placing sandbags along the top and bottom of our wings and measuring for deflection. We also tested our control surfaces to make sure we got enough deflection in our flaps and ailerons to sustain certain maneuvers. And we also used a thrust stand generator to make sure our propulsion systems could support both vertical takeoff and regular flight, with each system producing of about 9.5 pounds. And here you can see our hover test to make sure that we could safely hover before we transition into regular flight.
So having completed our VV&T test, we felt incredibly confident in getting this thing up to get in the air and actually fly. And at first it looked like it was actually going to do that. But as you'll see in a second, or I guess in a little bit, we suffered kind of like a crash. Unfortunately, it didn't break anything critical. All of our electronics survived. The only issue is, as you'll see here, we kind of do a backflip. We get a little tail heavy, and we end up losing a few of our, I think it was the rods, the carbon fiber rods that hold our propellers up. And back inside. We managed to rebuild. You can see here we got to get caught up with the draft. It was really windy, as Team ULFR stated. We managed to stabilize the plane and kind of get into forward flight. Unfortunately, this one came out a little out of left field. We end up losing power completely, like to all of our motors, and we kind of go nose down again. This one was a little more catastrophic. We end up losing our wing, I think a couple of propellers, and actually caused a fire because our LiPo batteries exploded. But yeah.
So some other challenges that we had throughout the manufacturing process, there was actually two main ones. One being that our wire management was a big concern. So when we were actually setting up the entire aircraft, we suddenly realized that we had no space to put the wires anywhere. So we had to go back into our CAD for the wing box and actually install a large enough hole that will be attached into the center of the fuselage and the wing itself. So all the wires will just be routed into that point, and it just spreads out all the wires evenly, and it makes it easier for assembly. And another thing was that for our wing itself, we had some issues with the installation of the motors. So whenever we installed the motors on, there was some unfortunate twist that would be caused by the weight of the motors themselves. So we had to install a bar that would go across the wing. But due to that, you get a lot of aerodynamic concerns. So in order to actually mitigate the effects of the aero caused by the bar, I installed and we researched different ways to do it. And we ended up coming up with slats that would just maintain the aerodynamic performance.
All right, with that being said, wrapping up this presentation, just some overall lessons learned. I think the big one that we learned really quickly this spring semester was to prioritize designing for manufacturing. Our actual CAD model and real life prototype look very similar. However, we did a lot of wire management. We ultimately had one of the most complex planes, I would say, in recent years. We had over like 15 wires per wing due to all of our servos, flaps, ailerons, tilt motors, motors themselves. So ultimately, we should have prioritized that more in the fall semester to make our lives a little bit easier in the spring semester. And I think one overarching concept for us as a team was, like I believe Team Greenwing said, you're expected to fail, and we obviously did fail. I hope you guys come and check out our poster to see what's left of our aircraft and our video of our crashes this afternoon. The big thing for us was a lot of times as engineers, we would sit down and we'd have conversations. We'd have like 2-hour, 3-hour conversation about how to solve this problem when one of us could have just been doing the math and the work behind it in the first place. Because if you learn and you try it out, it doesn't work, then you always just know that for the next time that you can go and attempt that problem yourself. So with that being some conclusions, some unfortunate flight tests results limit our actual analysis of our design feasibility. Ultimately, we wanted to deploy a quote-unquote pest deterrent, and while we weren't able to do that, I think if you were underneath that plane, you would have wanted to run away too. I think us and Team ULFR were in that situation. Ultimately, Team Aero Havoc did live up to their name a little bit more literally than we anticipated. Hopefully with some of the results that what happened, we exposed some flight test issues about mid-pines. I know some other groups talked about bumpy runways and whatnot. Hopefully some of the problems that we ran into might lead to a better airfield in the future, who really knows. But ultimately our structures lead and Cam and Daryl did do a pretty good job, because while our aircraft did survive two of the probably worst crashes you'll see for a senior design aircraft, most of it is still intact, and if we had a little bit more money left and a little bit more time and, I guess, desire overall, we could rebuild it within the next few days, but ultimately we were out of budget and without an airfield to fly in. So with that being said, thank you all for your time today. Thank you, Joseph, specifically, and the fire department. But if you have any questions, please come by our poster this afternoon, and I look forward to the rest of y'all's presentations. Thank you.
Taking the photos over there.
Over here, I think.
Hey guys, we start off the space section now. Should I wait for the photo? Oh no. Yeah, so I'm just gonna, I'll give the mic to team Cleo Satra. The team lead is Nick Lawton, and they are one of the 7 teams who got selected for the NASA mission concept. So I'll hand them off to them. Speak into the mic.
Okay. Hello and welcome. As Sridhar said, my name is Nick Lawton. And we are Cleo Satra, and that stands for Computation in Low Earth Orbit, Satellite for Reliable Accessibility. And we are here today to talk about our CubeSat. So we'll start off with our personnel. Like I said, my name is Nick Lawton. I'm the project manager and payload lead. Over here we have Will, who is the thermal lead. We have Eve, who is the structures lead. Mason is the communications lead. Alex is the ground station lead. Ben is the power lead. And Mohammed is the mobility and attitude control lead.
So our main focus was why Cleo Satra, and what we did with this design was find a way for reliable radiation protection for using commercial off-the-shelf electronics on current satellites or a new architecture. And this has a lot of usability, such as DoD interest in using swarms in space or AI in space. So we're looking at a way to find reliable radiation protection for commercial off-the-shelf electronics. So that brings us to our mission overview, which we determined was the space industry needs a way to provide reliable radiation protection for commercial off-the-shelf electronics. And we're doing this with a 3U computational satellite. We are going to use existing rad-hard techniques to improve current design, and we will measure the effectiveness of our chosen shield.
Thank you. So as Mason just mentioned, our main goal with Cleo Satra is to test new methods of radiation protection for electronics in space. And the way we'll do that is by having an experimental setup in our CubeSat, where we have 2 different commercial processors. One will be shielded from radiation and the other will not be, and act as a control. So the idea is that the control processor will start to degrade faster and output errors in the data that it is relaying with the ground station. We can track the rate at which those errors occur and compare it between the 2 processors, and hopefully determine that the shielded processor performs better over time. And we will also be tracking the amount of radiation that is present at every moment in time. So our target orbit is circular with an altitude of 1,000 kilometers, which places us in low Earth orbit. The images you see here are from SpinVis and SDK, which is software that allows us to simulate and estimate the conditions in our orbit. So we found that the most prevalent type of radiation in LEO is from proton and electron interaction, as well as galactic cosmic rays.
So this is our ConOps, or concept of operations, and it begins with rideshare into low Earth orbit, where the satellite will then be ejected via P-pod into and detumble into its specified orbit. Phase 3 will see the solar panels as well as the antenna deploy, and then phase 4 will see the radiation testing begin, as well as relaying the information back down to the ground station. Phase 5 is the end of life, which will then see a drag sail deploy for deorbiting.
So here we can see our two CAD models. At the top we have our full-scale space grade design, and at the bottom we have our prototype. Our prototype excludes components such as the drag sail, the communication antennas, and sun sensors due to space grade commercially off-the-shelf components being harder to acquire, much more expensive, and a lot smaller. So our main goal for our prototype was to focus on the core parts of each subsystem.
So the structured subsystem makes up the main body of the CubeSat, and as such, it must remain stable for the entirety of the CubeSat's mission. It must also provide an interface for all components from the other subsystems to mount to. So the way I designed the subsystem was using aluminum 7075 for the 12 panels that make up the walls and the 4 brackets that make up the corners of the frame, along with 2 3D printed end caps. Additionally, all our subsystems had to go through verification testing to test our designs. The way I did it for mine was using tensile stress testing as well as ANSYS Mechanical for stress simulations. All my tests were successful.
So the driving requirement for the thermal subsystem is made basically to keep all the internal components of the CubeSat within their operational temperature range, and this will be done, or this was done via a thermal coating which will provide heat protection, a temperature sensor and electric heater which provide heat production, and then a deployable radiator with heat sink to provide heat dissipation. And each of these were verified, as well as the orbital environmental simulation with success.
The driving requirement for power was providing sufficient power and storage and generation for all the electronics on board. The solution for this was using solar panels to charge up 5-volt system as well as a 12-volt system to provide the necessary voltages for the various components, as well as using lithium-ion batteries as they are providing good power density. The verification took place with using simulation to check the solar radiation received, a 12-volt system check, as well as a solar panel check to check voltages and amperages.
Moving on to the payloads design, we needed processors that were both commercially available and fast enough to actually detect radiation-induced errors and log them within enough time. And so I chose, through trade studies, 2 Raspberry Pi Zeros. And additionally, for redundancy, a watchdog circuit, which is controlled by an Arduino, which will actually reset any halted processors if they become bogged down from radiation. Logic level converters are used to actually communicate between those boards so that one doesn't break. And then finally, a radiation sensor that actually senses the data, or senses the radiation between the 2 processors so that we can verify when radiation actually occurs. As for the algorithm for controlling these processors, it needs to be robust and actually detect the errors virtually. And we do this with checksums during the transmission of data from different boards, which is an encryption to verify if anything has changed. And we'll use system health checks to verify that the processors are still running and that everything is on. And then finally, the watchdog timer, which uses the previously mentioned circuit to make sure that the processors can be reset if they do become bogged down. At the bottom of the screen, you can see an example of what it would look like if a critical radiation error actually occurred in our system. And above that are power consumption curves to verify the power consumption of the processors as they were published. For the radiation shielding, we wanted to investigate a novel shielding that was both lightweight and could efficiently protect the processors. Through trade studies, we determined that NCSU had developed a conformal coating which is doped with heavy metals and acts as a radiation shield for their nuclear reactor. Thank you. The conformal coating is like a rubber coating that's painted on electronics, and it's infused with heavy metals like tungsten oxide. The picture you see at the bottom is actually a 50% infusion rate, where we use a 60 to 70% rate for our space-rated design. And over on the right-handed side of the graph, you can see the top 2 lines are actually the expected radiation absorbance from the coating that we were using, and below that, the bottom 2 lines show the industry standard of aluminum shielding right now. So it acts much better.
So the communication subsystem main requirement was to ensure reliable data transmission of all air logs to be sent to the ground station. So this solution uses a NRF24L01 transceiver, as well as a Arduino Uno R4 to communicate with the processors on board, as well as a 16:2 LCD screen to display any values we read on board. And the verification testing for this subsystem used fault detection with air generation from the ground station, as well as a up-lake and down-lake latency test with the ground station.
So the goal of the mobility and attitude control system was to accurately determine and correct the satellite's orientation. Our full-scale design consisted of an IMU, sun sensors, 3 magnetorquers, and 3 reaction wheels, but we scaled it down to 3 BLDC motors, each aligned with the X, Y, or Z axis. These motors are controlled by an Arduino that's constantly receiving yaw, pitch, and roll angles from the IMU. Every time the orientation of the satellite changes, the corresponding motor activates to correct it. We can also see an example of the pitch correction data log here. And the motor torque and IMU data were verified through numerous experimental tests and simulations.
So the goal for the ground station is to set up a low-cost and functional setup for testing radio frequency transmissions with Cleo Satra. We do this by using another NRF 24L01 transceiver, which operates on the 2.4 to 2.5 gigahertz range. It also provides a 2 megabits per second data rate. That communicates with an Arduino Uno R4, which manages the data, and a laptop is used as the main power and interface for interfacing with the ground station. The 2 verification tests were the command upload test and the ground station to CubeSat range test. So here you'll see 3 visuals that kind of display all of our systems. On the left here, we have a wiring schematic which shows our 2 payload Raspberry Pis, our Watchdog Arduino Beetle, our thermal control system, and our mobility and attitude control system. In the middle here, you'll see a schematic for the communication system, which is very similar to the ground station system. And on the right, you have a functional block diagram for our full-scale UNP space-grade design. This shows our future expansion on our subsystems that we see.
For the manufacturing process, for the structures, we had to drill the holes and cut the panels in order to make the design structure. As well as for the payload, the 2 Raspberry Pis were connected with the Arduino Watchdog. The conformal coating was procured through the the nuclear engineering department here. For the thermal, we applied thermal coating to 3 faces on the CubeSat, as well integrated a temperature sensor and then a heater on the battery packs to ensure that the battery packs were to the right temperature, as well as a power required that the batteries and solar panels were integrated, as well as all the connections to the various electronics. For mobility control, the motors and controllers were connected, and then the IMU and Arduino were integrated to ensure that that data was being transmitted and then acted upon. The communications had Arduino and the RF sensor integrated, and then also made sure that it connected with the ground station, as well as output to an LCD screen. And then the ground station also had one of the same transceivers, LCD screen setup, as well as integration with the comms on the CubeSat itself.
Here we can see the final integration of all of our subsystems. If we look at the image on the left, we have the solar panels at the top, and then behind those wires, right below the solar panels, we have the payload and the communications Arduino. Then in the middle, we have the 5-volt and 12-volt power system, and then at the bottom, we have our attitude and control system.
So this shows our radiation testing results, which will, and you can see in the middle a jump in spike from the background radiation when a potassium-40 sample was introduced to the radiation sensor. And this will simply confirm radiation values in orbit, as well as with the information relayed from the unshielded and shielded processor will determine the success rate and the protection value of our payload. And further testing will be done in the NC State nuclear reactor.
So here's our budget breakdown. Of the total $2,000 we were given, we spent all but $12. The largest contribution was the mobility and attitude control system, followed by the structure of the satellite, and then ultimately followed by the power system.
And to conclude, we just want to say that Sridhar also mentioned this at the beginning, that we were selected from 7 other schools in the nation to represent NC State at the UNP Mission Concept Program. This is actually an internship for the summer of 2025 where we will work on refining our mission concepts or our mission concept overall, and actually refine our system design at a subsystem level. Also, on top of this, we are currently registering a club, an experimental nanosatellite club at NC State, to further our work in the coming few years and actually hopefully launch this by 2027 or 2028. We want to also thank Dr. Aweri, Sridhar, our TA, Dr. Bigham, Dr. Hayes, Patrick Hartwell, who was the PhD student who designed the conformal coating, and then NCSU MAE, our department, and UNP, the University Nanosatellite Program, who selected us for funding. So thank you, and we are Cleo Satra.
Yeah, 10 seconds, but you're good. Next up, we have Team Smart. They're also a satellite team, and the team lead is Zumi. Let me just open up your...
Does this one work? Hello everyone, we are Smart Squadron and we will be presenting SmartSat, which is the Soil Moisture Assessment and Response Tracking CubeSat. So this is just a general outline of the presentation that you're about to see. I am Zumi, the project manager and the ground station lead. We have Dylan, the thermal and financial lead, Jameson, the structures and mechanisms lead and the test and safety lead, Sam, the payload lead and the CAD and simulation lead, Jack, the GNC lead and systems engineering lead, Waylon, the power communications and data handling lead and the communications liaison, and Zach, the propulsion and manufacturing lead. This is just kind of a image of the team layout and how we work together to efficiently develop the CubeSat. So SMART is intended to aid in disaster relief during hurricane season. Outside of hurricane season, it is intended to aid in agricultural development and DoD terrain scouting. This is kind of an image of what our satellite would be creating compared to a regular camera.
So here's a quick look at our functional block diagram. This showcases how each of the different subsystems interact with each other. It's a lot of interfacing with the power systems and the communication systems. So a quick look at our concept of operation. Our satellite will first be ejected and launched, and then it'll enter the detumbling mode, in which the reaction wheels in the GNC system will stabilize the satellite, in which it'll deploy. After it's stable, the deployment will deploy mainly the solar panels and the radar. And then from that, we have 3 operational modes, starting with sun pointing. So it's important to get our satellites, to get our solar panels pointed at the sun to maximize charging. Once they are fully charged, we will also be in earth pointing mode, which is basically just pointing our radar at earth at the specific spots we want. And then after that, we also need to be talking with the ground station, so we need to be able to point at specific spots on earth. And then after that, we will be end of life using propulsion to deorbit our satellite.
So our design solution process, we kind of started out with a different topic, and we've ended up changing focus. Originally, we wanted to monitor rogue waves and report those to ships and Coast Guard. But due to how unrealistic that was, we've shifted over to doing soil moisture research and soil moisture mainly. And in our off time, we want to help with like Department of Defense terrain scouting and other similar things. This is our design solution. This is our actual like theoretical CubeSat CAD model. On the next slide, we have our final prototype, which is what we've constructed using our budget. This is a list of parts and things we've used. Some notable things are the cantennas, and the my favorite is the handmade solar panels from our power lead. Very cool. Manufacturing, we're going to go through. We have a lot of pictures from our manufacturing. We're just going to kind of talk over them. For propulsion, we have a system of tubes and a nozzle. It's all store-bought, so it can be easily assembled, and we added some L-beams to fit it in the CubeSat there. I'm going to pass it to Zumi for ground station.
So you can see the progression of the ground station. On the left is the prototyping stage. I then proceeded to clean it up, and then you will see the final prototype in the poster session, which is on the right.
So for the manufacture of power and communication, on the far left, you can see our hand-built solar panels, and then we have a driver circuit for the propulsion system, as well as the power delivery board, which is all hand soldered. And then you can see the process of wiring the whole system together.
All right, and for the prototype payload on the left picture, you can see how we started out. There's four main parts of the payload. There's the two antennas that you can see in most of the pictures, the voltage modulator circuit and the video amplifier circuit, which is self-soldered by Whalen as well in that second picture. And it's a little small, but in the first one, there's the RF part of the circuit. It's kind of towards the bottom of that image, and it's designed to function in the 2.4 gigahertz range.
So a quick look into the GNC system. The first picture on the left is kind of our original design, in which had to be updated to increase the moment of inertia for our system to try and induce a greater torque, which is that second picture. And you can see before we have our frame fully structured out, kind of like the basis I was going off of is that cardboard box, and you can see it interfacing with my laptop, which shows the data readouts, and then all the way on the right is the final design. So we're using photosensitive resistors to kind of track the sun, as well as a gyro to track the force induced by Earth, and that gives us ability to stabilize our satellite and point at wherever we want it to point at.
So yeah, like my colleagues mentioned, we are a 12U satellite, so that results in a 20 by 20 by 30 centimeter configuration. To the bottom left picture shows the CAD drawing of the actual frame and the cutouts for the antenna, like for Sam's payload. And the bottom panel has a cutout for the nozzle, which is for Zach's propulsion, and then a cutout for the sun sensor for GNC. And this middle picture shows the location of where the welds are going to go to help connect all the struts, the top and bottom panels, and the side panels. And then this final picture on the bottom right, I'd like to give a special shout out to Jacob. He was able to get this welded for us. So
this is the thermal design. So on the pictures on the left and the right are heat sinks attached to electrical components that we deem that are very critical for our CubeSat or that tend to overheat really quickly. And then the picture in the middle shows the heater and the thermocouple, and the heater will turn on during like cold cases where it drops below 5 degrees Celsius, and then the thermocouple just reads off the temperature.
So the first screenshot on the left is a data file that was transferred from the CubeSat to my ground station. It is just a text file, but it would be an audio file in the future. And then the screenshot on the right would be the initialization of all the hardware that is connected to the ground station. Normally, it would just say that the data was saved to the data storage system.
To test the propulsion, we have two long videos that are a little too big for the presentation. So instead, we got a picture of it working there. We had a structural and leak test to make sure that the air was actually making its way through the entire propulsion system. And then we also had an integration test to make sure it worked with the power. As you can see by the capacitor we launched out of the nozzle, it is functional.
All right, so for the power verification testing for the solar panels, you can see we have them charging in direct sunlight. They're generating about 22 volts. And then in the middle is our MPPT board. That stands for Maximum Power Point Tracking. It's basically an efficient way for solar panels to charge the lithium-ion batteries. And here we can see them that the MPPT board is functioning properly. And then on the far right, we can see the driver configuration for the heater.
All right, and for the big final test for the payload, we wanted to demonstrate the SAR functionality of the radar. In case you don't know, synthetic aperture radar means you're moving a smaller radar system along a path tangential to your target to create a synthetically larger antenna. This allows for higher resolution images. That's what we're doing in the middle picture. On the left picture, we have a faux ground station processing the data similar to how the full-scale design would be. And it's really hard to see, but those two little red dots at about 250 feet correspond to those two clumps of trees there. and the rest of it is the rest of the tree line. So we did actually manage to capture a synthetic capture radar image with these literally soup can waveguides.
Yeah, so for the structures testing, courtesy of Dr. Ware, I was able to get into the structures lab to do these tests on the 30 centimeter strut. Mainly, it was just a bending moment test, just to see what force would cause bending to occur within the strut. Basically, what we're looking for in this top graph on the left, when the lines start to curve, that's when the strut starts to bend. And what we found is that a force of around 330 newtons causes bending. And the functional requirement for the structures was that the CubeSat frame has to survive a load of 5 Gs, which would be invoked during launch, which was equivalent to around 334. So ultimately, this test is still successful because the test was under the assumption that the 5G load would be applied directly to one strut individually. But since there's a total of 6 struts, this load would be dispersed without the frame. And this middle picture basically shows the setup of the testing being done, and then this final picture on the top right shows the full deformation of the 30 centimeter strut. I'll pass it on to Thermal.
So the first picture is the heater being measured with an infrared camera, and at 12 volts it measures to about 307 degrees, which is more than enough for the heater. And then the 2 pictures on the right is for the thermocouple, is that little setup, and that picture right there shows that the thermocouple is able to successfully measure temperature. So to quickly sum up system integrations is all of our subsystems are connected together and they function properly, with power being able to meet all of the power demands for each subsystem, and including circuit protection and power regulation. And our main component of the SAR testing has gone really well and shows great potential for that. So for the budget, our 3 biggest contributors are the payload, power, and structures, with the rest of the budget sprinkled throughout the other subsystems. And there is $100 remaining for additional checks and all that. So in conclusion, we think our prototype shows great potential for future iterations of our design, along with our prototype meeting our design requirements. And we think that this CubeSat will lead to future CubeSats. Thank you for listening.
The next 4 teams are the rover teams from the space section. And to start off the rover section, we have team Loopy Marte, and the team lead is Carson Drummond. Let me just... Is it muted? No, I can... Oh, I was just holding it.
No, I meant the computer.
I don't think so.
There we go.
Let me just open up your... Yep. Slideshow. Where's slideshow? Where's slideshow?
Yeah.
I should just do that.
Hey, good morning, everybody. We are Team Loopy Marte, and we were tasked with a Mars precursor campaign. So we're essentially looking to fast track getting humans on Mars for a permanent presence. And our proposed solution is Chris. It's a rover, and that is the cave habitability researcher for initial settlement. Quick outline, we're going to go over the personnel and everyone's subsystems. Then with the rovers, you kind of have these 2 separate projects. One is the space grade rover, and then one is the actual prototype, because unfortunately we don't get hundreds of $1 million to play around with. We get about 2,000. And then we are going to get to the crux of senior design and reflect on what we learned. So I'm Carson Drummond. I'm the project manager and payload lead. We have Dylan Curtis, the ground station lead, Dylan Burdett, structures lead, Alex Thill, power systems lead, and Maverick Trumpler, the mobility and attitude control lead. And we have Matthew Dickerson for data and comms, and Nicholas Barber on thermal controls and survivability. For the organizational structure from the top down, we start with the MAE department. So we have Dr. Ware, Dr. Wary, and our TA Shri. And then we roughly split it up into these 3 different subsystems. But we want to emphasize that There's a lot of co-working here. You know, everyone using electronics has to rely on Alex per se with the power systems.
We built Chris to explore caves on Mars and lava tubes for the purpose of potential human habitability. More specifically, we're going to be reading radiation levels, geological investigations, and the general cave structure, with the hope of potentially living out of these caves rather than bringing pre-built structures from Earth, greatly reducing cost and mass.
So this is our concept of operations for this mission. Provides an overview of our mission, which begins with phase 1, landing on the Martian surface in the Hellas Planitia region of Mars, selected for its many surface accessible lava tube and cave entrances. It will be landed by SpaceX's Starship. It will navigate autonomously across the surface of Mars to pre-selected lava tube and cave entrances. It will enter the cave and autonomously gather geological information, radiation scans, and LiDAR point clouds to map the interior of the cave and determine the habitability characteristics of the cave. It will then take this data outside of the cave and uplink it to the Mars Reconnaissance Orbiter, where it will then be relayed to NASA's Deep Space Network ground stations here on Earth.
Here's our functional block diagram, and hopefully y'all can see it here. Our start point is the plutonium-238 that powers our power systems, and you can see how that flows throughout all of our subsystems in the form of power, data, heat, and torque, and all to produce the results that we send back to Earth.
For our prototype solution, we had to scale down quite a bit. We couldn't rely on a $100 million RTG and maybe some of the cool technology that NASA has available. So we simplified down just to focus on the mobility and capability of traversing in a rough terrain like sand. So we implemented our 6-wheel rocker bogie design, which allows us to make sure that all 6 wheels stay in contact with the ground at all times. NASA claims that this works and is functional up to 45-degree inclines. We didn't push it that far. We just pushed it about 15 degrees, but also demonstrated stability and integrity in really rough sandy hills. We also purchased a depth camera that was going to be used for obstacle detection and pose estimation. It ended up being a little more complicated to implement. And then we also have some just kind of cool dummy payloads we created with 3D printing to kind of make our rover feel more like a space-grade rover. For the mobility and attitude control system, which I kind of spearheaded, the design ended up being a lot more complex than was actually feasible to implement in manufacturing. So we designed path planning with a probability-based method, which kind of randomly samples nodes in your operating space that you predefine. And then you use those randomly sampled nodes to kind of construct a straight line path going from your start point to end point. This ended up being a lot harder to implement with just the kind of budget and time we had. And then to maneuver, we used differential steering just for relative simplicity. Given the capabilities of our suspension, we felt that differential steering, which just involves moving the wheels forwards or backwards, would be more than enough to kind of get us to where we need to go. And this allows us to maneuver without having to individually change the heading angle of any of our wheels. On the prototype, we ended up kind of having to focus more on just getting the rover working and kind of had to push aside some of our autonomous navigation capabilities. So we used a Raspberry Pi, wired it up to some cheaper motor drivers. We had more expensive ones at first, but the radio communication was not working. So we had to kind of just, a last-ditch effort, find some cheaper, more simplified options. We were able to get a live stream of depth data from the depth camera. The only problem is when I installed some of the kind of dependencies and Python packages for the depth camera, they just did not install correctly, so I only had the live stream, but I couldn't actually receive data or kind of use data to implement any autonomous navigation capabilities.
Yeah, so for the structure subsystem, we had 2 main parts, the chassis and the suspension. For the chassis, it was made up of aluminum extrusions framed together with corner brackets and bolts and nuts. For the outside of that frame, you have aluminum plates to fully enclose the chassis. And then for the suspension, we're made up of 3D printed parts at the joints being PLA and ABS materials. And then the legs of the rover are aluminum.
For the payload, the main component was this mast cam. We designed it in-house, mostly 3D printed with the integration of a camera, a laser pointer, and the 2 servos. And this was to simulate laser spectroscopy, which is essentially zapping rocks with a laser, and then you can determine their geological makeup. So looking at the bottom left picture, you can see the square hole is for the camera, the circle hole is for the laser, and then the 2 servos on their separate axes provide 2 degrees of freedom.
Now, for the data and communication subsystem, we have 3 options. The first of which is the most convenient. It's the one that we use most on campus, where we have Wi-Fi. So it's Wi-Fi reliant, and basically we just screen share to the rover's onboard computer and control it from our laptops. But we also have a pair of radio transceiver modules to use away from Wi-Fi. These are a little bit less reliable, so we went with the secure shell. We also have another pair of nearly identical transceiver modules, but they are equipped with a low noise amplifier and a power amplifier, as well as an external antenna to help boost the range.
Yeah, so for the ground station subsystem, we went with virtual network computing, which is VNC, fancy way of saying we access the Raspberry Pis on board of our rover remotely. And one of these windows is used to control the navigation script on the Pi. The other was used to access the depth camera data, which you can see the live stream of on the bottom right there. We also use network hotspots to just give us some versatility in where we can use the rover, inside or outside, whether and not being reliant on the NC State network environment.
For our thermal control and survivability system, we used 6 Noctua 60mm fans, 3 for intake, 3 for outtake. That provided more than enough cooling for all of our critical components, preventing overheating and disruptions in the system. To prevent debris from getting into the chassis, which is a major consideration with dust and sand, especially in the sand pits, we used a 3 micrometer stainless steel mesh that we had on both intake and outtake, proving to be extremely effective.
Yeah, so for power, basically we have 3 circuits. Each one has a lithium polymer battery. You got a power switch, 10 amp fuse, and then a little DC to DC buck converter, which basically takes a higher voltage and drops it down to a lower voltage.
We're going to quickly go over some of the VVNTs that we did. First of all, Alex did a battery capacity test where he would just draw a certain amount of current out for a set amount of time and then determine how capable our batteries were for the mission. For motor torque, we lifted a 20-pound bucket with our motors to make sure we had enough torque. We had beam strength for the chassis on the Instron machine. Nick did some fan cooling where he would draw current just to check the power requirements for that. And then lastly, we did data transmission, which we're checking to make sure the motors can communicate. Go means go, stop means stop. And then here, we thought it was important to highlight our design evolution. In the top left, that is from our very first meeting, and that's just in the library on a whiteboard, the beginnings of Chris. Then we kind of see the CAD start to take shape. And then lastly, at the very end, that was used for our Rascal proposal in the competition of our space grade design.
Yeah, so here you can see our final product, kind of the inside of our prototype rover. The 2 Raspberry Pis, the LiPo batteries, motor drivers, the 6 motors going to each of the wheels that were designed specifically for sand, and the fan cooling system as well. On the right, you can see our prototype rover out on the sand volleyball court, testing the capabilities of the rocker bogie system, which you can see in action here, keeping all 6 wheels on the ground at all times. This is kind of our one small step for man moment, seeing our footprint on the sand volleyball court. We also threw him in the sand pit and tested the 15-degree incline, which he handled successfully.
Yeah, so one of the best things about this project is that you get to learn through doing. I mean, and with learning, you're going to have some setbacks. So some of those setbacks that we had is that we had some integration issues between the Raspberry Pi and the depth camera. Also, some budgeting issues, purchasing things we didn't need. Those motor drivers we never ended up using. And then some of the structural components we had to redesign multiple times. We had some cracking when some of those joints were load-bearing. We had some cracking, so we had to make them a little bit thicker. And then for our final test runs, everything performed well, so that was good.
So we did do some things right. We utilized the fuse, which I blew when I shorted a circuit with my body. Shocking. We 3D printed a load-bearing joint shaft, which you can see on the bottom there. Basically, we added a rib to support the load. And then we used the high torque motors with low RPM so that the wheels weren't spinning super fast, so they'd grip the sand and make good contact with the medium. And then the differential steering, as you saw in the video, worked really well. So we're really happy with that.
And just to conclude, we kind of want to make our case. We think that Chris offers a very low risk and high reward Mars campaign and is a relatively computationally simple as far as autonomous rovers go on Mars, and will be able to answer a lot of questions and provide a lot of insight to future Mars campaigns.
Next up, we have Tenacity with their rover Remora. And the team lead is Alex from Tenacity, so I'll just hand it off to him. You have a PDF? Is that right?
Yeah.
Okay.
Slides there.
It's all right. We'll work with that. Yeah, do you want to zoom?
Is that not supposed to be a PDF?
No. It's okay.
It's okay.
We'll work.
That's so my bad.
Okay. Thank you everyone for being with us today. We are Tenacity. Today we'll be going over the rover equipped for maintenance operations and repair assistance, also known as the Remora.
So just our presentation outline, we'll start with the personnel and structure, then go into the problem and mission description, detail that further with the ConOps, then talk about our functional block diagram, and then break it down to our design solution going subsystem by subsystem, and then we'll take you through some manufacturing testing highlights before we end off with our conclusion. So this is our team. To my left, we have Alex, our structure and mechanisms lead, as well as our project manager. Paige is our financial lead, our mobility and attitude control lead. Aramis was our manufacturing lead and power systems lead. Tony was our systems engineer and payload lead. I am the test and safety lead, as well as our communications and data handling lead. Brooke was our communications liaison, our thermal control and survivability lead, and then Will was our ground stations lead.
Here you can see a diagram that shows an overview of the communications for this project. This begins at the top with the management of Dr. Iware and Dr. Ware and RTA Sridhar. They funnel information to our team leader, Alex, which then he is in charge of dispersing between the different systems and tasks that the individual team members took on.
Okay, so to give a quick overview of our project, the main focus of our project was assisting in future Mars missions. So the purpose of our project is to ensure the safety of crew members and maintain mission operations through the preservation of Martian equipment. And so we identified a need for a system that will allow astronauts to repair mission essential machinery to a functioning level. And so we designed an autonomous Mars rover that will facilitate repairs and maintenance of Martian equipment to a high level of precision.
So breaking down further and illustrating that through our ConOps, so Remora would start in its docking station at its home base until it would be alerted of a problem by the ground station. It'll then autonomously navigate to that incident site and assess the situation, take some pictures, videos, and send it back to the ground station for review. The ground station would then review those images and see what tools, what parts does the repair need to be fulfilled. So would relay that to Remora. Remora would then autonomously navigate back to the home base where parts and tools are stored. It would retrieve those parts and tools and then autonomously navigate back to the incident site and deliver them to a specialized repair robot to complete the repair. Stick around until that repair is done, and then take some pictures and videos, send that back to the ground station, make sure that repair is all good, and then autonomously navigate back to the home base where it waits for another mission.
To go in a little more detail about the operations of Remora, this is our functional block diagram. It's organized by the different subsystems and the components within them, and there's different arrows that demonstrate the flow of power, communications, or power commands and data between the different subsystems and components.
So we constructed a CAD model to showcase all the different subsystems integrated together. So you can see here we have our chassis, wheels, motors, power, and in addition we outlined the prototype specifications, including dimensions, weight, and power requirements, and we'll now go into further detail with each subsystem.
So for our guidance and navigation, we primarily use an ultrasonic sensor to collect data about our surroundings. We also have a camera where, in case the ultrasonic sensor breaks, it allows an operator to assume manual control of the rover. To map the environment, we programmed a Python code to convert the radial distance gathered by the ultrasonic sensor into an occupancy grid, which is on the bottom image top in the blue, where the blue line is. After that, we programmed an A-star path planning system to find the optimal path around the obstacles. And then to keep track of our movement and position in the map, we supplied power in certain time intervals in order for the rover to move 20 centimeters forward at a time or backwards, and to also turn 90 degrees in either direction. We primarily use the forward movement unless there is an emergency where the rover needs to back up.
So moving on to power, we used 2 LiPo batteries. At some point we had 1, at some point we had 3. We settled on 2. And our system operates at 11.1 volts with 10.4 amp hours of current. Everything is wired in parallel on the breadboard. Most notably our 6 motors for the wheels, you can see in our little diagram. And then we used a buck converter to drop the voltage to 5 volts to power our Pi, which takes care of powering the arm as well as our sensor. As for charging, we have 2 methods of charging. Our main method is using the balance charger by plugging into a wall. This would be the analog to charging at the home base for our rover. And then we do have a secondary backup charging mechanism using the solar panel. So if our rover is outside and we need a charge, we can do that as well.
So moving on to structures and mechanisms, the structure system consisted of the chassis, suspension, and the wheels. The chassis and suspension were both constructed from aluminum 5052 due to its manufacturability. The chassis consisted of 4 side plates and 1 base plate held together by 8 L brackets located in the corners. And then the suspension consisted of 2 static components and 2 rockers, which were connected through a bronze bearing and a shoulder screw to enhance mobility. And then finally, our wheels were 3D printed using PLA filaments, which were connected to motors using shaft blocks, and every wheel had a chevron V-tread to enhance mobility.
Our original design solution for Remora involved the use of thermal paints, specifically an emissive white paint and absorptive black paint. However, we decided that for the prototype level, this was not necessary. So in our prototype, there's a few different design changes that just help actively or passively regulate temperature. This includes Raspberry Pi heat sinks. In addition, the aluminum chassis functions as a cold plate for a lot of the electronics, and we chose not to have a back cover on our systems to help stimulate heat dissipation.
So for our ground station, we had 2 design solutions. The first, and it offered the most control over the rover, was remote access through the VNC. So basically with that, it allows us to control all 6 motors on our payload, which is a robotic arm. We can move the rover manually instead of autonomously if we want to. We can see a live camera feed of the camera that's on board the rover. And additionally, we can see the 2D maps that are generated from the ultrasonic sensor while it is navigating autonomously. Now, sort of a contingency is we have our communication development kit, which uses this development kit consists of a development board and an antenna and a transceiver, one hooked up to the Raspberry Pi on Remora and the other hooked up to the ground station's laptop. And This offers extended range, so it can go up to 11 kilometers, but unfortunately it allows us to have less control over Remora, so we have to send specific commands that tell the Pi to run a script, and then data is recorded using Excel files.
So kind of bouncing off of that with the communications and data handling subsystem, same thing, using that developmental board with the transceiver and antenna combination, up to 11 kilometers, which is a pretty good range. It uses the XBXR868 module with an antenna system, and of course working on the Raspberry Pi serial. It's a radio frequency communication on the high frequency band, and it allows seamless communication between the ground station and the Raspberry Pi. And on the right, you'll see a little flow chart that shows the different data flowing through some of our subsystems, looking at storage, looking at transmission, looking at receiving commands, as well as our guidance, navigation, and control.
All right, so moving on to payload. In order to get Remora to be able to move, pick up objects and put them in the storage bay, we went with a 6 degree of freedom robotic arm that has a maximum reach of 1.2 feet and a max load of 0.5 pounds when fully extended. It is controlled by 6 servo motors attached to a servo motor driver attached to the Pi. At the front of the end effector is a high definition camera for automated movement and navigation. All this is coded in Python. And yeah.
So moving on to manufacturing and testing. These are just a few highlights of our manufacturing. Starting in the top left, we have our suspension and our wheels. Our wheel design changed a few times, but eventually we did settle on that chevron pattern that you guys saw earlier. Bottom left, we used quite a bit of the machines, like the drill press and the milling machine, to make our chassis and suspension. And then top right, we were originally going to use stepper motors for our wheels, but last minute we changed to DC motors and they worked a lot better. They were easier to wire, so I'm glad we did that. And then we used like a spare buck converter to monitor our voltage, so that way we could quickly monitor our battery life at a glance. We decided to keep it on our final prototype. Some BVT highlights, we have our charging test. I went outside with the solar panel and I was able to step down the voltage to power the balance charger and charge the battery. Our arm test, done very early on, trying to make sure that our arm can pick up objects. You see in the photo we have a screwdriver. We were originally going to build an arm like from scratch, but we switched to the kit because it was really hard. And then we have our launch loading simulation. We can withstand a 6G gravitational load, which is nice. And then as you saw earlier, our path planning, this is what it looks like on the computer.
And then as we went through, we were able to do some more advanced stuff. Here's a little group photo with our onboard camera set on a timer, click of a button, and we were able to take that picture. And then on the right, you have a remote control dashboard, what it looks like on our side when we're controlling the rover. Movement with WASD, arm with the arm 6 servos with sliders, and then a button to take a picture.
For our final flight tests and results, we were able to navigate through harsh terrain such as sand, mulch, and tall grass. We were also able to move the robotic arm to pick up spare wheels, rocks, or tools. And then our GNC system successfully navigated around a fixed optical course as well as a simply dynamically changing environment.
So to attempt to sell you guys here, I want to tell you about the value of Remora, why this mission objective is valuable. So as you might guess, interplanetary missions are not that cheap, and Remora's ability to extend the mission lifetime of future Mars missions would be extremely valuable because it could save engineers lots of time and money and millions of dollars. And just for an example, the past rovers Curiosity and Perseverance both experienced issues during their mission lifetimes. For Curiosity, it was wheel damage due to the rugged terrain on Mars, in addition to a drill malfunction. And with Perseverance, they had clogged soil sample tubes, both of which could have been helped by Remora. If they couldn't repair it itself, it could have acted as a additional set of eyes for engineers to view the problem and hopefully solve it quicker.
So to quickly summarize, the Remora is an autonomous Mars rover that will function as a repair bot in future Mars missions, ensuring the safety of crew members and the longevity of operations. Thank you.
Next up, we have Team Brover. And the team lead is Adam. So just hand off to him.
Ready? All right. Good morning, everyone. We are Team Brover, and we are really happy to show you what we've been working on for the past 8 months. So our team was tasked with designing and building a Mars rover with a certain mission. And so our mission was to drill and extract ice cores and then transport that. So we're going to talk about that in a bit. I'm going to introduce the team and our work breakdown structure. So my name is Adam. I'm the project manager and the propulsion lead. Over here we have Nick, and he's our payload lead and our survivability lead. Alex is our structures lead. We have Bazad as our communications lead, Connor as our GNC lead, Giovanni as our power lead, and Steven as our CAD lead and manufacturing lead. So for the organizational structure, we have our customer, Dr. Ware, our course instructor, Dr. Ware, and our section instructor, Sridhar, up at the top. Below them is me, the project manager, and below me, the 5 roles that I kind of oversee is administrative, systems, structures, test and safety, and manufacturing.
And so kind of going over what we wanted our project to be. There we go. When we first decided that we wanted to do, well, when we had our Martian project, we wanted to do ice core drilling. And so if people don't know what that is on Earth, they'll go to glaciers and they will drill into them. And they can drill like kilometers deep, and essentially you can get like a deep dive into the past. You can look at the environment and things that have happened in the past on Earth. And so we want to do that on Mars. And so doing that, we can get a better view on what happened in the past on Mars, and well, we can also see maybe if there's life, if there was life on Mars, such as that. And then so there's a lot of current limitations on Mars. Like firstly, the deepest they've ever dug is like 2 inches, I'm pretty sure. So this is going to be a huge change where for the full scale, we could be digging up to kilometers deep. And then there's also a huge gap in the ability to understand the evolution of what has happened on Mars. And so we kind of want to give scientists more depth and view into what has happened. And so what our mission is essentially we want to start at a home base and then travel to the drill site and then go autonomously navigate back and forth, continuously drilling into the same hole until we get to the deepest part we can get, and continually analyze the ice that we receive and see what information we can find.
So, sorry in advance, I've been losing my voice for the past 2 days. But, so as he was saying, the goal of Frosty is to retrieve ice samples to determine any past tectonic or organic activity, basically life or water. And as he was saying, our mission is broken down into like 3 core components. The first one is a custom chassis and wheel design for rough terrain. The second one is autonomous navigation and obstacle avoidance. And the third one is the payload retrieval, which we'll talk about later.
So here you can see our functional block diagram, which is a high-level overview of all of our subsystems and how they interact with each other in terms of power, data, and communications. This just kind of shows how the whole system works as a whole. So looking at the payload is comprised of the linear actuator used to move the drill up and down. Then there is the motor that is used to operate the linear actuator, the motor for operation of the drill, a chuck which is fastened onto the shaft of the drill and then connects onto the 1/2 inch hollow core bit, which has a 1/8 inch shaft, which then goes into the drill chuck. and a 3D printed motor mount for the drill motor. So looking at the manufacturing of the payload, started with creating the linear actuator, which was built based on the instructions provided by GoBuilda, which is the vendor that we used for the linear actuator. The drill was constructed by fastening it onto the linear actuator using the aforementioned mount. The 3D, sorry, then the drill chuck is added onto the shaft of the motor, and then the drill bit is then put onto that chuck. So for testing, we started with a sand drill test, which involved spinning up the rotor to our desired RPM and torque, and then descending it all the way full depth into the sand. Then we did the ice test, which involved also spinning it up to the torque required to descend into the ice, and then descending it to the full depth of the coring bit.
All right, so for thermal survivability, this consists of a white spray paint that goes onto our aluminum external panels. These were cut with a reciprocating saw and to triangular pieces, and after that they were sanded down and spray painted. It also consists of cooling fans that will go inside or on the chassis, glued down, and are positioned so things like motors, batteries, and other sensitive components can be cooled down. And then for the testing, we wanted our internal temperature to be below 40 degrees Celsius, so that was set as the upper limit for the paint test. And for the paint test, it consists of a thermal imager that I had, a heat lamp, and then two other small aluminum components, one that was sanded down, painted, and another that had nothing done to it at all. And you can see on the top right, there is a plot with the blue line showing the painted component. You can see it performed very well. It only increased about 2 degrees Celsius, while the other component with nothing done at all increased above 15 degrees Celsius. So that test was very well for the paint. And then the other test was for the cooling fans. This focused on the linear actuator motor, as we saw it increase in temperature much more than any other component. So I set up fans around the linear actuator motor, ran the linear actuator until the motor got to a higher temperature, wait for that to stabilize, and then I turned on the fans. And you can see in that bottom graph on the right, after about 1 minute, there's a drop of 7 degrees Celsius, and then about 22 degrees Celsius stable for the rest of the test. So that fan showed to work very well for that.
All right, so onto the propulsion system, which encompasses the wheels, motor, and the suspension system. So for the suspension system, we went with rocker bogie design like every other rover group. We made that out of strut channels, and we connected those strut channels together with steel angle brackets and hinges. That made it a lot stronger than like using plastic. And then for the wheels, each wheel had their own motor. There were 6 wheels, and each wheel was 3D printed out of PLA. And we added some grousers on the exterior of the wheels, which helped provide sand traction. So the motors that we went with have a max RPM of 435 and a max torque of 1.8 Newton meters. So we had a few design changes going into the manufacturing and testing phases. So the first one was that the wheels that I had originally designed were way too small. The rover was sinking like really deep into the sand. It was probably like 2 or 3 inches. It was like 50% of the wheel's diameter. So I increased the wheel's radius and the wheel's width. And it sunk a lot less. It was about like 10% of the wheel's diameter. And then to improve rigidity, we reduced the wheelbase and the track width. And that helped the rover turn, and it helped keep its legs up while it was driving. So when we were doing testing, the motors did a really good job. We were actually able to scale up a 20-degree incline, which can be seen as the middle picture. We drove it on some grass, and then the mobility, the rocker bogie suspension system also did really well. We were able to drive it over some mounds and in some rough sand and things like that.
To briefly talk about our structure, our chassis was made from PLA, 3D printed PLA, I-beams, flat plates, and C-channels, sort of JB welded and epoxied together. And then we had aluminum panels on the bottom and top of our rover to protect everything from the sand and to give it a better look. We also added strut channels and braces around the outside of our chassis and towards where the suspension connects into the chassis to help resist some bending moments and provide more stability for the rover. Overall, our prototype was a 1/4 scale of what the overall rover would be, so our prototype being about 1 meter by 1 meter by 1 meter means that our full-scale design would be about 4 meters by 4 meters by 4 meters. Again, as I talked about before, with our manufacturing, we use JB Weld and 3D printing for our chassis. We determined that the chassis would be probably our most critical loaded component, so we did a finite element analysis on that system, found that our margin of safety would be something around 27 or 28, so it's very safe. And we also conducted a static loading test by adding weight on various points of the actual builded chassis, measured the deflection, and those results matched what we found from our FEA.
So for the power and electrical, my subsystem consisted of 6 lithium-ion batteries in a wiring harness. As you can see to the right is the wiring schematic. And during this process, halfway through, we switched motor controllers. And so the challenge I faced here was creating one-off adapters and so having to solder everything. So for the testing that I did, I had to test each individual battery for 3-4 hours, testing the voltage and the current, creating the power curve that you see there. Surprisingly, almost every single one of the batteries overperformed the expected values except for one battery. But based off the results of the second test, that was not a concern, as I was able to continuously run everything, including the drill, for 1.5 hours. And during the process of recording footage for the con-op video and doing a final test, Frosty was able to last like 5 hours, which I thought was pretty impressive.
Looking at the GNC solution, we had a time of flight sensor, we had motor controllers, we had Arduino, and I synced up to the motors as well. We also used an A-star program for navigation like the other group. Some key design changes, we switched time of flight sensors at one point, it didn't work. And then we changed motor controllers. We dummied down our rover a little bit, so we got to use smaller ones, which was nice. And then for testing, the big test I had was an obstacle identification. I pretty much just made sure the time of flight worked. It did, and it turned off a motor whenever I got my hand too close to it, which was nice. And then the second test, which you can see in the bottom right, it was to see if the A-star program worked, and it did. It basically could find the shortest path throughout the grid I set up. It's a little hard to tell, but the ones represent the open slot zeros are the ones that represent like an obstacle, and so you can see the path with the hashtags.
All right, for the communication system, we used 2 main parts. The first one was the same onboard computer as we have for the GNC, the Arduino Mega. The second one was the transceiver, which was used to transmit data from the rover to our ground station. As far as for the manufacturing, it involved excessive amount of wiring, and let's just say we are also glad we had that covered by the panels. And it was also writing the code to establish the communication between 2 systems. For the testing, we wanted to make sure that our ground station is able to receive the time of flight sensor reading from the rover. And just to remind you what time of flight sensor is, just measures the distance between the rover and the obstacle. And that video kind of shows the number. These are some of the specs of the final prototype. I'm going to go over the main ones. The main one is the weight. It kind of weighs about 41 pounds. It has a top speed of 1.7 miles per hour, and the battery lasts somewhere between 6 to 8 hours.
Yeah, so just to wrap up, we had a few key accomplishments, which is that we successfully designed, built, and tested the functional ice core drilling rover. And we definitely overcame some very difficult challenges that we were able to fix. So we're really happy with that. So there's some impact with our rover, and that is that it's going to fill a critical gap in Mars exploration and accessing deep ice for climate and life studies. And then everyone gained some hands-on experience in design, manufacturing, and testing. And we want to give a special thanks to Aware and Shri. Thank you.
Next up, we have Team Iris, and the team lead is Chadwick.
What's the Google size, right?
I was thinking 5 minutes, then 2 and then 1.
Sounds good.
Stay in your time. You got this.
All right. Thank you, everyone, for joining us today. We're excited to present IRIS, the Interplanetary Rover of Integrated Science. Here's a brief outline of what we're going to be talking about today, as well as our personnel, followed by me, the project manager, Mira, our financial lead and payload lead, Brady, our manufacturing lead and avionics lead, Cora, our test and safety lead, as well as our CAD and simulation lead, Jose Leah, systems lead and propulsion and structures lead, Charvi, our communications lead and power lead, and Roy, our stability and controls lead. Here's the organizational structure, which kind of depicts how we communicated throughout the duration of this project, as well as the project description. Understanding the potential for human survivability on Mars is one of the most critical challenges that we've had to face this year. As we move closer towards the sustainability of crewed missions beyond Earth, we must assess environmental risk like the availability of water, presence of organic compounds, and harsh terrain conditions. IRIS's main mission is to determine this survivability on Mars by detecting these organic compounds in the Martian polar regions. Through this, it's going to be able to autonomously map and navigate the polar terrain, collect surface ice samples, and assess these atmospheric dust conditions. Here's the mission description, as well as our ConOps, and the functional block diagram, which all lead to the control lead, our control system, which kind of allows for the autonomous factor of everything.
So here's an overview of our design solution. IRIS is approximately 30 pounds, supported by a rocker bogie suspension system and aluminum chassis. As you can see in the exploded view of IRIS, we have our robot arm, sample collection system, and camera and LiDAR system on the exterior of the rover. And then on the interior of the rover, we have our power and avionics system, which Brady will talk about now.
All right, so I'm going to give a brief overview of our avionics system. So the avionics acts as essentially the brains of our rover. So it takes inputs from all of our peripheral devices. So think of like cameras, LiDAR, or ultrasonic sensors. And then it processes all of that data onto our Raspberry Pi. And then it sends output signals to our different control devices like our motors so that we can drive. So one of our driving requirements was autonomy. So we went with the newest Raspberry Pi, which has 13 trillion operations per second of computational ability. So that's like, think of like a modern self-driving car. It's on that scale. It's a lot of computational ability that we have. And then on the right, you can see our avionics schematic, which has our wiring diagram based on all of our different subsystems. And here's some of our manufacturing and testing from avionics. So in the top left, we have one of our early stage wiring pictures, and then bottom left, we're working on it. And then we also have verification testing for both the camera and the LiDAR on the right side. Okay, Mira's going to talk about our payload.
Okay. So our payload consists of two main components, the arm and the sample collection system. Our arm has 6 degrees of freedom and has a 16-inch reach with a claw at the end to be able to pick up these samples. And our sample collection system is it has 5 compartments for storing each sample individually, as well as a sliding lid to protect the ice samples from dust, debris, changes in the weather, stuff like that. So looking at our manufacturing and testing for the payload, specifically the arm, it was pretty simple because we purchased a third-party arm. So most of the manufacturing process actually just came from connecting the aluminum brackets and connecting the high torque servo motors to the joints, and then integrating that entire system into our avionics to be able to control it. And for our sample collection system, that is actually completely 3D printed because we had specific design and functional requirements that would just be met if we 3D printed that part. Looking at testing, we tested our arm by picking up different simulated ice samples of weights and sizes to make sure that it could actually pick it up and maneuver it, which it could, as well as making a kinematic model to display the orientation of the arm. And then lastly, for the sample collection system, as previously stated, we're working with polar ice. So we want to keep those samples as solid and in their original form for as long as possible. So we tested different kinds of insulation.
So on to the design solution for our structures. For our main body, we went with a pre-manufactured aluminum chassis, some design rocker bases that interface with our suspension system, and an acrylic chassis top to allow you to see all of our beautiful internals. For our suspension, we went with the tried and true rocker bogie system, which we 3D printed ourselves. And then our center of gravity, which changed from our original CDR design. It's a little leftward bias, which affects our driving capabilities and has a bit of a front bias. Now onto manufacturing and testing. With that pre-manufactured chassis, we cut and drilled holes for all of our avionics and payload. We 3D printed our rocker bases and rocker bogie components, performed any necessary post-processing, such as sanding, resizing of holes, and soldering in inserts. And then we assembled all of those components together and integrated them with our motors and wheels, and then attached that to the chassis. Oh, you go back. You can see in the bottom right a picture of all of our parts. We went to Hill about 30,000 times, so became friends with all those people. We also did some chassis loading validation and verified that with actually just putting our components onto the chassis. And as you'll be able to see, it is not broken, so that's good. And then now onto the design and manufacturing for propulsion system. Our system takes inputs from our avionics and GNC systems to translate and steer IRIS towards its mission objectives. It does this with 6 3D printed wheels designed to traverse on soft and compact terrain, interfacing with each of our motors via a set screw connection. Our motors are 6 150-to-1 gear motors with an RPM of 59 and a torque of 79 kg/mm, which integrate into that rocker bogie system using motor mounts and interface to the wheels using those aforementioned set screws. For our testing, you can see through the video, that was one of our first tests. Kind of looks like a Honda Civic that you see at 1 a.m. A lot of camber, not intentional, sadly. Later on, we did some testing in the Marco pit, did some sand testing, some incline testing, and also took it outside. We also did some motor speed testing as long as endurance and torque testing, where we confirmed with our vendor quantities that we matched our RPM.
All right, so for actual operation on Mars, IRIS will utilize an MMRTG, which is a radioisotope thermoelectric generator to help power batteries, and that has a really high NASA technology readiness level, which is why we chose it. It's also the preferred choice over solar panels for Mars missions going forward, because there have been a lot of issues with dust storms that we anticipate during our missions that cause issues for communications with solar panels. So we are, for our proof of concept, utilizing lithium polymer batteries, and this is because MMRTGs usually cost a couple $1 million. So we are going to be using 2 lithium polymer batteries with a power distribution system that focuses on isolated routing. And we do this so that each subsystem is powered individually, so that one loss or one failure in a subsystem doesn't impact the rest of them, and we can ensure continuous operation. Also, our initial design was for 3 batteries, which was based off of our power budget that we created, but because we have a really great avionics system, thanks to Brady, and a really good wire management system, we're able to succeed with just 2 batteries and provide more than enough power for all of our subsystems. So on the next slide, I have a couple of the data that I got from testing these batteries that required a lot of discharge and charging cycles. I monitored on each of the 6 cells for each battery how much voltage drops over time, what subsystems cause that to drop, how much energy we can get, and the overall battery discharge rates to create the most effective power system. Moving on, for our communications, we are using a Wi-Fi adapter, the Panda wireless adapter, along with a virtual cloud network. And something to highlight here is that during testing, we simulated data loss and made sure that Iris is self-aware and can tell ground station, hey, you lost some data at this exact time. Please check for data corruption, and then also continuously try to reconnect to the Wi-Fi.
All right, this year's Senior Design Challenge emphasized autonomous operation, and so consequently the guidance and navigation systems were key components of the IRIS rover. In particular, we wanted to achieve global terrain mapping, which involves not just being able to avoid obstacles in the vicinity, but to be able to traverse terrains, remember the obstacles, and plan optimal paths. Our navigation system consists of IMU-based pose estimation, with a number of algorithms, including the magic filter, double integration, and an ICP SLAM algorithm for terrain mapping, which works on LiDAR scans. The guidance algorithm takes those grid maps, convolves them, and converts them into terrain grid maps where a modified A-star generates paths between primary waypoints, and an iterative ray tracing algorithm reduces the nodes on those paths. So if you go to the next slide, what you're seeing here is a partial floor map of the first floor of Engineering Building 3. On the right, the SLAM map, which was composed entirely by Iris, was stitched together from 31 LiDAR scans at the positions indicated. On the left, the corresponding terrain map contains 640,000 nodes, and the terrain pathway that you see there was generated via the path planning algorithm, maintaining 1.5 feet of distance from all obstacles, and taking the rover from the main stairs to the Entrepreneur Drive exit in just 7 secondary waypoints. So continuing through the GNC, we're continuing to develop this, mapping in 3D environments. So with the existing system, we can do 3D IMU-based pose estimation for the elevation, pitch, and roll changes. And the ICP SLAM system can be extended to 3D, working on sectional LiDAR scans. The particular difficulty here is developing the dynamic scanning frequency, which will have to adjust to account for scanning steeper terrain changes. So overall, this is a very successful, we're very pleased with the guidance and navigation system. It satisfies every single design requirement written for the Iris rotor prototype.
All right. In conclusion, the current iteration of IRIS is capable of autonomous navigation and mapping, sample collection, preservation of samples, data communication, and multi-terrain mobility. Special shout out to Dr. Ware, Dr. Awari, and Sridhar, our TA. And be sure to check us out later today where you can see IRIS in action. Thank you.
Finally, we have the NASA student launch team, Team Taco Lycos, and the team lead is Caitlin Young. I'll hand it over to her.
Hello, good morning. Welcome to our presentation on our NASA Student Launch Project overview. Go ahead. So my name is Caitlin Yunt. I am the team lead. Our structures lead is James Hawley. Our recovery lead is Trent Kels. Our aerodynamics lead is Aubrey Sprouse. Our payload structures lead is Ryan Keever. Our payload software lead is Connor Swanson. Our payload electronics lead is Samuel Pattison, and our integration lead is Abigail Coupler. So the NASA Student Launch is a year-long competition between 60 national teams, about 60, to design a rocket and payload every year, and this is launched, tested, and built to be launched final competition on May 3rd this year. Some competition requirements are launching the rocket to a specified apogee that we predict at the very beginning of the year, and then we design it, test it, and fly it to this altitude. We must return the rocket back to the ground within 90 seconds, and we must hit the ground with no more than a kinetic energy of 75 feet per second. Some other requirements that are specified based on the payload change every year. Everything else basically stays the same, but it depends on the payload challenge. So we have to design a payload that is capable of collecting relevant landing and flight data and then transmitting it on the 2-meter band to a specified NASA receiver upon landing. These payload challenges try to mock future NASA missions to give us some real-world experience. We build a subscale and a full-scale vehicle throughout the year. The subscale is a maximum of 75% dimensions of the full scale, and our full scale can be seen on the right there. We'll also have it at our poster session later today. We'll have both of them. We write reports that are graded by NASA engineers, and this makes up most of our score in the competition. We have so far written our proposal, our preliminary design review, our critical design review, and our flight readiness review. We have 2 more documents before the end of the competition. So far we've written 850 pages, and with all of documentation, working on milestones, working on prototypes, and our launches, the team has dedicated, senior design team has dedicated approximately 4,200 hours to this project thus far. Next, we have the launch vehicle design overview presented by James.
So this is our launch vehicle. It's about 8 feet tall with a 6-inch body diameter. It weighs about 40 pounds sitting on the pad, depending on how much ballast we decide to fly. And we're powered by an L-class solid rocket fuel motor. We designed and analyzed the vehicle using various software programs. We did initial layout using OpenRocket. We used RocketPi and RAS Aero for mission performance evaluation. The entire vehicle and all subassemblies were modeled in SolidWorks, and we used various ANSYS tools for load simulations. The vehicle itself is primarily made out of fiberglass, although we do have some birch plywood and aluminum internal structural components. To manufacture the vehicle, we used a wide variety of tools and methods, including using a lathe, manual milling machine, water jet cutter, CNC router, 3D printer, lots of various hand tools. We have 4 sections from nose to tail. We have a combination nose cone and payload bay, followed by a main parachute bay, followed by our combined avionics and air brakes bay, and then lastly a drogue parachute bay and fin can. These are some key design features of our vehicle. All the way forward, we have an adjustable ballast system. This allows us to fine-tune our stability margins by shifting the vehicle CG as needed. We have a simple and very elegant payload retention system that allows for seamless integration of our primary payload with our launch vehicle. We also have an onboard camera that allows us to visually verify the flight performance of the vehicle, the air brake system, as well as the recovery systems. Amidships, we have our air brakes module that deploys drag fins with an active control system that allows us to fine-tune our apogee in order to maximize our altitude points at the competition. And all the way at the aft end of the vehicle, we have our removable modular fin system, which is a structural assembly, multi-purpose assembly that provides fin and motor mounting. We have a thrust plate on the end for even application of all of our motor thrust forces directly to the end of the airframe, and a custom motor retainer. Next, Trent's going to talk about our recovery system design.
Yeah, so the primary purpose of the recovery is obviously to get the rocket down in one piece. We accomplish this using a dual deploy recovery system with a drogue parachute that's deployed at apogee with a backup charge 1 second after apogee for redundancy. The vehicle then descends under the drogue parachute configuration as pictured in the first diagram to the right until 550 feet where our main parachute is deployed with the backup charge set to 500 feet. The vehicle then descends as seen in the configuration on the far right image into the ground, and all sections of the vehicle remain tethered together throughout the entirety of the flight. It was designed such that the shock cord lengths are maximized to reach 10 feet of separation between all sections, just to prevent any of the sections from colliding during ascent and to make sure that the shock cord doesn't get caught up and the parachutes perform as expected. The parachutes for the competition, we use a 24-inch Rocketman parachute as our drogue, which is protected by a Nomex blanket, as well as a 96-inch Iris Ultra compact parachute as our main parachute, protected by a deployment bag. This parachute combination was calculated and confirmed through verification flights to provide us with a kinetic energy at landing below 65 foot-pounds and a descent time below 80 seconds, maximizing the points you receive in the competition for our recovery system. Kind of the heart of the recovery system would be the avionics bay. This is where we hold our altimeters and our GPS, which really control the separation events and ensure proper functionality of the system. This is located at the forward end of the AVAB, and all the electronics are mounted onto 2 flat plates with the altimeters on the top plate, as well as the GPS, batteries, and switches on the bottom plate. It was designed with some small holes in the sides of the plates to allow wires to run freely throughout the system, as well as to connect our E-matches to the forward and aft bulkheads. This was designed such that it would maximize separation between the altimeters and any frequency emitting devices, that being our GPS and our air brakes, just to ensure that there's no EMF signals that could accidentally trigger deployment charges early. The bottom plate's also lined with aluminum foil just for some extra shielding to meet all NASA requirements. Up next will be our mission performance predictions presented by Aubrey.
Stability and motor selection are important components of vehicle performance. Per NASA requirements, our stability must remain above 2.0 calibers and thrust-to-weight ratio must remain above 5.0. Multiple simulation softwares are used to determine and verify these values. This launch vehicle configuration has a stability of 2.0 calibers on the rail, and using the L1520T motor, we have a thrust-to-weight ratio of 8.75. Using various simulation softwares, predicted apogee can be simulated. Additionally, flight profiles can be developed, predicting altitude over time, velocity over time, and acceleration over time. Different qualities, such as wind speed, can be implemented into these simulations. This is an example of a flight profile, and different predicted apogees are on the right-hand side. The payload design will be presented by Sam, Ryan, and Connor.
So our structural components for the payload are 3D printed with PETG filament. These components include the sled, which retains the electronic components. The top bulkhead has a ventilation fan. The bottom bulkhead, which holds our stem knot housing, and the capsule shell, which interfaces with the launch vehicle. All of our electronics are mounted to the sled using heat set inserts with nylon standoffs and screws. And our payload is 17.25 inches tall and 2.55 pounds. The Simcraft rests between the nose cone permanent ring bulkhead and removable bulkhead. The removable bulkhead attaches to the nose cone with 2 1/4-inch hex nuts and is fastened to the threaded rod. And the Simcraft sits flush inside between the permanent ring and removable bulkhead throughout the entire flight.
This year's payload design is the wireless APRS relay for high altitude environmental and atmospheric data, or WARHEAD for short. This features 2 CPUs, the first being Raspberry Pi and an ESP32. And shown on the right in this figure is a functional block diagram of how the components interact. The system is designed to operate fully autonomously, but also allow for remote overrides with the ground station. It is comprised of the fuse, switch, charge, and torch subsystems. The fuse subsystem is our subsystem that collects data for transmission. This collects 9 data points using 3 onboard sensors and operates at 125 hertz. And the switch subsystem is our team's transmission subsystem. This is controllable via the ground station. Shown in this image is the manufactured warhead. On the left is the front, and on the right is the back. The front of the warhead consists of the fuse subsystem and the primary CPU, and the XP, which we use as the ground station. The ventilation fan is wired directly to the Raspberry Pi. And on the back side, both of the batteries. The first is a 2S lithium polymer battery, and the second is a 4S lithium polymer battery. Both of these are wired to the same dual pull-pin switch, which allows them to be toggled on and off from the outside. And the SA858 is the team's primary transmitter.
The air brakes is an active control system whose purpose is to guide the rocket to a target height. All the components are 3D printed out of PETG, and the main purpose, or the way we predict our maximum height, is by curve fitting the vertical acceleration of the rocket. The IMU, we take the onboard data from the IMU and convert it to a global frame and just get the vertical acceleration that we are experiencing. We fit a curve and extrapolate that curve to apogee, to our maximum height, and we can extrapolate the future velocities and height at any given time. We plug this data points into our control scheme, which will allow us to deploy our air brakes if we are overshooting our target height and retract them if we are undershooting. As seen in the graph on the far left, this was a successful implementation during a flight test. After 2 seconds of motor burnout, we predicted an initial apogee of 4,136 feet, and the fins successfully deployed and increased the drag of the rocket, slowing us down to our target height of 4,000 feet, where they then retracted. And this led us to a final apogee of 3,962 feet. The middle graph shows the fin deployment overlaid with our vertical acceleration, and we see during deployment there's a spike in negative acceleration, and subsequently we can find that we have a 0.2 increase in the CD of the rocket.
So next up we have our launch results. So the first one we had is our subscale flight, which basically is a 2/3 scaled model of our full-scale design. This occurred on November 16th and was deemed successful by the NASA panel. We went to about 1,500 feet at about 10 miles per hour with a stability of about almost 3, just under 3. On board, we had both payload and air brakes. We had a preliminary payload design that basically allowed us to test our sensor functionality for data collection, and then we used the data there to further in VV&C testing later. Additionally, our air brakes, it functioned as intended. However, it was slight delay in our software, which led to the air brakes not actually going out at the correct time. Next, we have our full-scale demonstration flights, both vehicle and payload, to verify to NASA that both our vehicle and our payload are safe to use on the launch field in Huntsville. Our vehicle demonstration flight occurred this past weekend on April 5th, and we're waiting for confirmation about the success of this, but all of our descent times and our kinetic energy was underneath both underneath the payload and vehicle requirements for NASA. Additionally, our payload demonstration flight occurred on April 5th, and during this attempt, we had a slight software error on takeoff. However, it was deemed successful by our NASA panel during our FRR presentation, and it actually successfully worked this past weekend. Our air brakes worked on all 3 flights, and it deployed successfully, and we actually got to a point where we were about 42 feet off of our predicted apogee, basically a 2% error in our calculations. Other than that, that is the end of our presentation. We have a lot more details on this project, so please come by our poster presentation, but thank you so much.
Are the videos going to play if it's like this and not a Google Doc?
Can you open that?
We can find trash bag.
Yeah. We're used to getting scrappy.
Is it possible to open it as a Google Doc?
Yeah, we can do that.
I should have shared it with
But
you.
like, if this is fine, like you can just open the video and explain. Is that okay? And then get back to the presentation again.
We can try it. It's just the videos were recorded in vertical,
Okay.
and it's going to play it in horizontal, so it's going to be very blurry. But when I submitted it on Moodle, it was as a Google Doc.
Let's try that.
It's on day one.
We need to go back. Log in again.
Fought it for 48 hours. Just figured it out.
Sebastian, can you get my phone?
Can you come this side? I'll just like this. Is that okay?
Yeah, this is perfect.
Alright.
I can talk into that, right?
Yeah, you can do that.
I'll give you guys the mic and I'll just talk into that.
Greetings to all present. I am Lavya Sharma and I have been the TA for the multi-rotor section. And I'm introducing my first team, which is the DBVF, and their name is Ignis Dominatus, and the team lead is Bryce Scott. So, handing over.
All right, thank you for being here, everybody. Good morning. So, as our TA mentioned, we are NC State's first ever design build vertical fly team. And yeah, welcome to our presentation. So this is a presentation outline. Our presentation is going to be a little bit different from all the other teams here. Unlike pretty much every other team, we don't have a hypothetical ConOps. We have a real ConOps that we actually flew. And unlike the other competition-based teams, we have already competed in our competition. So instead of focusing on VV&T and manufacturing, we wanted to show you guys exactly how we performed in the competition. So this is our team. There's me, Bryce Scott, project manager. To my left, Hunter Power, systems engineer. Reed is our manufacturing lead and our pilot. Greg is our financial lead, and Sebastian is the test and safety lead. It's our organizational structure, pretty similar to every other team here. Everyone reports to me, I report to Lavia and Dr. Iwari, and then our customer is the Vertical Flight Society. So the purpose of this project is to design an eVTOL aircraft to simulate a wildfire mission and to compete in the 2025 DBVF competition. And the need is an advanced eVTOL aircraft that can provide rapid autonomous aerial support for wildfire management and accurately deliver the payload. So our mission statement, Team Ignis Dominatus, which means mastery of fire. We will design and build an eVTOL aircraft capable of meeting those requirements. And our goals are to complete at least one lap autonomously, take off and land vertically, and deliver the maximum payload.
So for our concept of operations, in our case, it's a two-part system. We had one flight mission, dubbed Flight Mission 1, or FM1, and then we had Flight Mission 2, or FM2. For Flight Mission 1, we had 4 landing zones and a home base. Each of them were a 10-foot diameter, and we were required to fly the first lap, landing in each zone and continuing to the next one, coming back to home. All subsequent laps were flown with just a landing at home and were done for completion of number of laps. For Flight Mission 2, the zone diameters were reduced from 10 feet to 3 feet incrementally, and it was required that we drop our payload in each zone, and the scoring was based upon the number of bottles, the water bottles, our payload, that were dropped in each zone, and the scoring increased with the smaller diameter zones. Our functional block diagram shows the setup of our aircraft. You have got the ground station with the transmitter, the pilot input, and our computer system. And on the aerial vehicle, we had our flight function systems, and then we had our flight director that was responsible for autonomy and flight control.
For our design solution, we went with a hexcopter platform. We considered briefly quadcopters and octocopters. However, we settled on a hexcopter mainly for the added stability and also like fail-safe. Should we lose a motor, we still have 5 more that we can safely land with. Overall dimensions, we made this within to fit within the 3-foot diameter, the smallest diameter zone, and the legs just accommodated slightly more than what the payload fit underneath. So some further drawings that we included here, just showing the overall dimensions. We included everything is just made out of carbon fiber, which was water jetted, and aluminum. During our faux fly, we were a little bit traumatized during flying just 3D printed platforms. So we wanted to have a higher factor of safety using only carbon fiber and aluminum, minimizing the prints where it could be.
So for our propulsion system, everything was ordered from T-Motor. We got 16-inch carbon fiber props, 450 kV motors, and 60 amp ESCs. That offered us a solid 5 kilograms of thrust per motor and gave us a good overall thrust to weight ratio of 4-to-1 unloaded and 2-to-1 loaded.
So here we have the structures exploded view. Like Hunter said, we have a lot of carbon fiber. You can see the top plates, the top and bottom plates, which are water jet carbon fiber that sandwich around the aluminum arm mounts, clamping around the carbon fiber tube with the motor mount that Sebastian just showed on the last slide at the end of the motor arm. And then finally the landing gear mount, which is aluminum, and then another carbon fiber tube and a 3D printed foot. So again, the motor mount assembly here, it is just exploded. This was pre-purchased aluminum, a carbon fiber plate, fits the mounting pattern of those T-motor motors.
Our avionics stack was sandwiched between our two carbon fiber plates. In the center, you can see our flight controller that was mounted centrally in the aircraft. And then surrounding it were our 6 ESCs, along with any other flight essential items such as our remote ID or telemetry systems. The payload system was comprised of 2 carbon fiber plates. The bottom plate held each individual payload radially. There you can see we have 14 water bottles, which put us in the second position in terms of capacity in the overall competition. There's a small protrusion that pushes the water bottles out as our servo turns the bottom plate, and the water bottles run into that protrusion there that drops them sequentially.
So for day 1 of the competition, this would have been last Wednesday, I believe. A requirement to fly FM1 and FM2, like Reed spoke about, was completing ground mission 1 and 2. You can see the leftmost video here is us completing ground mission 1, which is confirming that we can safely control the aircraft both manually and autonomously, which requires us to take off, ascend about 10 feet, roll, pitch, and yaw the aircraft the directions that the employees directed us to, and then in addition to that, take off autonomously, begin transitioning or moving to a waypoint, and then cancel that autonomous mission, regain manual control, and safely land the aircraft, which Reed did. Ground mission 2 consists of a similar thing, but this is conducted fully loaded, so you can see the rightmost video. Again, we're kind of far back just because of the safety requirements. It's fully loaded with all 14 water bottles. This is when we began experiencing our first stability issues, which you'll hear a lot about, but we did successfully and safely complete both ground mission 1 and 2, which gave us 30 points and a successful check to fly FM1 and FM2 later.
All right, so day 2, we noticed several oscillations during flights, and so it became a troubleshooting day. We decided to talk with the engineers at the site that was being hosting the event, and they offered us ideas, and they told us basically it could be a tuning problem. So we decided to add a harmonic notch filter to try to get rid of the oscillations as it was flying. Eventually we decided to just scrap that because we hadn't tested it, and we went to a soccer field to do auto tuning and just try to problem shoot the whole drone. Eventually we noticed, well, Greg noticed, that as it was flying, the 5th motor was not spinning on par with the other ones, so we decided that to land the drone immediately and then troubleshoot whether it was a motor, ESC, or a power problem. After a whole bunch of swapping with motors, ESCs, the power distribution board, we noticed that it had to be a burnt ESC. So can't really fly with that, so we decided to make the executive decision of going to a quadcopter formation.
So before day 3, we had a long night in the hotel room. We disassembled our drone and had to reprogram the entire thing, pretty much scrap all of our autonomy and flight programming from the past 2 semesters because we had to take 2 motors off. So we turned it into a quad and then finally got a good pickup in the hotel parking lot with 4 motors, proved that we could still deadlift our 14 water bottles, and decided to call it a night. The next morning we woke up, as you saw in the first video, torrential downpour, terrible rains at 5 o'clock in the morning. We were supposed to be off the ground at 7:30. So when we got to the field, we wrapped our platform in saran wrap and confirmed that we were good to fly. Went out there, and because we technically changed configuration, we lost all of our points previously acquired. Regained them quickly by proving our stability in both ground mission 1 and 2. And then here in the rightmost video, you can see a successful fully autonomous takeoff and landing as it continued on flight mission 1 for extra points on the autonomous lap. We elected to, or actually initially, we were instructed that we would have 2 attempts, one where we could attempt flight mission 1 and one attempting flight mission 2. Upon approaching the flight line, we were told we had to choose between one or the other, which we took a huge ding on points with because we expected to have at least one opportunity to fly each with our new configuration. Due to a controversial call in landing zone 3, they said that we had not successfully landed autonomously within the landing zone, so we were forced to take over manual control and land 500 feet away in these small landing zones with nothing but verbal communication over a broken walkie-talkie, trying to get them in the zones. But we did successfully get points on the board at the end of the day 3, despite all the setbacks and basically having 2 days that were awash. So, our attempt to channel the cardiac pack spirit might not have been the most successful, but we did, in the end of the day, not have the lowest number of points out there, and we're proud of what we were able to accomplish.
So thank you for listening to our presentation. I think that it may have been the result that we wanted. We showed up with the hexacopter, finished with a quadcopter. I think most other teams would have rolled over and not done what we had done, and I think that's the dedication of this team and these guys around me and all the preparation. So thanks to Dr. Iwari, thanks to Lavia for all your help, and we're very proud of ourselves. Next year, hopefully they do better than we did, but for our first time, I think it was pretty good. So thank you.
Picture. Act like we like each other.
I'm going to just introduce everybody, and I'm not going to say like a week. She's going to introduce us. I don't care what you do, as long as you know who you're handing the mic to. Who am I handing the mic to? You're handing it to me. Okay, so you send it to me.
So the next team from the multi-rotor section is the Future Flyers of America, and the team lead is Benjamin Ashley.
Good morning, everybody. We are the Future Flyers of America, and we have designed the Field Falcon, a multi-rotor drone for assessing farm conditions after severe weather. So going over everything, this is Andrew, Tyler, my name is Ben, this is Abi, Thomas, and Carson. For the organizational structure, myself and Abi are the project manager and communications lead, and we are the main point of contact between the course instructors, project customers, and faculty advisors, and we're responsible for disseminating and sending out all the information that the rest of the team needs to know. So our project is a part of the NASA Gateway to Blue Skies competition. For the 2025 project description, NASA challenged students across the country to develop a novel aviation system that can be used to improve the agricultural industry by 2035. And that was where we designed the Field Falcon. We came up with the mission statement: the Future Flyers of America will design a lightweight, battery-powered hexacopter UAV that will be used to assist farmers with pinpointing hazardous field conditions after severe weather. This entails supporting a single payload while collecting overhead images of the field and completing post-flight data processing. So some objectives and constraints that we had to work with are as follows. Some of the notable ones: we had to, our drone had to fit within a 5x3 by 2 foot volume. It had to be operated within a line of sight. And it has to broadcast a remote ID per the FAA.
So looking at the budget, we had a total budget of $1,000 to build our drone. The majority of that budget, about 34%, went towards the airframe materials with the carbon fiber center and the carbon fiber tubes. Another large portion of our budget went towards our camera, which is our main payload, so we wanted a high-quality camera that could take good pictures at the altitude we were flying.
Our payload is a Our payload is a single camera that is it's a high fidelity camera. They'll be used for capturing images and videos. Our first survey goal is to detect hazardous areas or obstructions, such as rocky areas or muddy paths, and then using the images and videos captured by the camera, we'll use it to determine vegetation analysis. We'll be using vegetation indices such as variable atmospheric resistance index and green leaf index to measure plant density, coverage, and health. Our functional requirements, we have 9 functional requirements which are used to guide in our design of our drones. I'll be highlighting 3 of them. Our first one is the Field Falcon should weigh no more than 10 pounds. It should be operable and assembled by no more than 2 people. And the Field Falcon should demonstrate stability in various agricultural environments and also in windy conditions. And this is our functional and form mapping. On top, we have our functional requirements. On bottom, in the colors, are the design requirements which are used to fulfill our functional requirements. and we see how the design requirements are connected to our physical subsystems.
So this is our concept of operations for a standard mission profile. It starts off with the prep and assembly phase, where we run through our pre-flight checklists and check things such as the battery voltage and that motors are spinning in the correct direction. This takes about 15 minutes. Following this, the next 5 minutes were spent either going over the mission profile with the pilot, if we choose to do a manual flight, or uploading the mission profile onto the flight controller if we do an autonomous flight. Then our flight time right now is about 13 minutes, so about for the next 13 minutes, we'll be flying over, surveying the land, taking video, and then it'll land back at the ground station where we will do post-processing and color indexing.
So a little bit of benefits to customers. Why should you buy the Field Falcon? It all breaks down to 2 points. It reduces risk and saves money. So the reduction in risk comes from the standard practices for surveying land after severe weather incidents. Normally, it involves either manually walking around a field or driving a tractor or other farm equipment around a field. Using a Field Falcon, this would reduce risk because of a reduction in human labor, and also it would reduce risk to farm equipment with the chance of it getting stuck, which would cost time and money to repair and get unstuck from conditions. It also saves money by being a much faster alternative to surveying land, and also it is an affordable option in the drone sector. So the functional block diagram for our project is here. You can see that the ground station, the payloads, and the vehicle itself are all connected through various wired and wireless power connections.
So when looking at the design solution, you can see two images, the left one showing the exploded view of our design solution, and the right one showing it fully assembled in a CAD rendering. Two important notes when looking at the design solution are the fact that we are using a Hexa-X motor configuration for the hexacopter, and that the battery is placed on the exterior of the frame, allowing us to make sure that we don't have excessive heat within the flight controller aspects. When looking at some of the electronics, propulsions, and structures, I would like to highlight that we are using a 10,000 milliamp hour 4S lithium polymer battery, as well as using a SpeedyBee F405 V3 flight controller and two 4-in-1 ESCs to power our motors. In regards to the motors, we are using six 650 kV motors to power the system. And looking at structures, some of the materials we use include carbon fiber and 3 different 3D printed plastics, including PETG, ABS, and PLA. Some important flight parameters and performance parameters include the fact that we are able to achieve the FAA limited maximum altitude of 400 feet. However, we don't plan on using that for most flight parameters. The maximum speed we were able to achieve during our flight test was just over 20 miles per hour. And we have an estimated range and coverage of about 325 acres based off calculations made from our flight test. So some other important parameters are that we have a height of just under a foot, allowing us to meet those volume requirements set by Senior Design, and we have a weight of just under 7 pounds, making it compact and light.
So looking at the manufacturing of the drone, starting off with the electronics, we 3D printed custom mounts to secure the electronics within the main frame of the drone. We then soldered all our electronics together outside the drone and placed them in the drone, checking continuity to make sure that everything was connected and sitting firmly. For the manufacturing of the shell of the drone, the carbon fiber main frame was cut out of 2 carbon fiber plates, and the connections and mounting for the drone were printed out of the previous mentioned plastic materials and were mounted to the carbon fiber using heat set inserts for secure fitting. For the verification test to make sure the drone functioned as desired, we performed a hover test to ensure that it would be able to loiter in windy conditions, which it will likely have to operate in. We performed a throttle range test to make sure that the input from the transmitter was properly received by the drone. We performed on-board sensor tests to make sure that the readings we were getting from our flight controller were accurate to what the flight controller was actually experiencing. We performed a remote ID test to ensure that we were complying with FAA regulations in transmitting a remote ID. We performed a finite element analysis on the arms to make sure that the carbon fiber tubes we selected were able to support the forces the drone would experience during flight. And finally, we performed a drop test to ensure that the landing gear could withstand rough landings by dropping it from 3 feet in the air.
Going over the risk management, we identified 10 different failure modes that the drone could experience mid-flight. Just highlighting 2 of these, R4 and R7, both representing either an arm breaking or battery loss. We came up with a risk management mitigation plan to address some of these more critical concerns, and all of these either ended up reducing the likelihood or severity of them. So in the case of R7 for battery loss, we came up with our pre-flight checklist and also post-flight analysis. That way, pre-flight, we check the voltage of the battery, as well as post-flight, we immediately plug back in the battery just to make sure that it's prepped and ready for the next mission.
When looking at the test flight and results, we have a video that shows we do not have a video that is working, but the video showed both the takeoff and reaching desired altitude. From this flight, we were able to look at many different parameters gathered from the SD card in the flight controller. However, for the sake of the presentation, we are only showing the flight path according to the GPS data, the altitude, speed, and the gyroscopic data gained from the flight controller.
So for image processing, we also had a video here to show the in-process image processing. I do not believe content was enabled, so we can't show it. But you get a still image of the VI green index. After the flight has landed, we post-process the videos to get a file that shows the land surveyed. In the post-processing, you're able to see areas of non-homogeny highlighted. This can really help identify mud areas, rocks that are very difficult to identify just looking at a green landscape and almost impossible to see from looking at the ground.
Since our flight test, we've considered some areas for growth, such as compiling the GPS and video data to make an accurate map of the terrain, automating flight for efficiency, and a gyroscopic camera mount for video stability. The Field Falcon was made as an efficient surveillance tool.
Thank you.
Get our videos to work on Google Docs. Can we just assign in that way? Perfect.
Yeah, do that.
Max, you want to sign in?
I just keep prompting you with the time.
Okay.
2 minutes left, 1 minute left.
We'll put it up here too, so that we can just kind of have it.
Now presenting Team Props and Crops, and team lead is Max Nanichka.
We're Team Props and Crops, and this is the Guardian UAV. I'm Max Nanichka, the team lead and payload and avionics lead. This is Blaine, the propulsion lead, Sata, the structures lead, Jared, CAD simulation lead, Kevin, the stability controls lead, and Landon, the aerodynamics lead. So with the reintegration of apex predators into national forests and parks, such as Yellowstone National Park, there is a need to be able to harmlessly and safely capture apex predators that wander too far and threaten farmers, livestock, and crops, so they can be subdued until the Forest Association can reintegrate them again. Our proposed solution is a drone that is capable of moving faster than the sprint speed of these apex predators while remaining just as agile as them. It is mounted on the underside with a net launcher that is capable of launching a net to entangle apex predators, subduing them.
Here's our proposed concept of operations. Starts with the pre-flight inspection to ensure flight readiness, using an external surveillance system detecting the target, taking off, adhering to FAA altitude restrictions, using the onboard camera and sensors to detect the animal, descending, maintaining or following the animal using the onboard systems, deploying the net, and using some sort of external system to relocate, and then the post-flight inspection. And then throughout the design process, we went through a few iterations, namely the change of the payload launch angles going from horizontal launching to straight down, the propulsion unit going from 8 rotors to 6 rotors, the flight controllers, we've gone through a few different ones, and the landing gear design to clear the payload.
This is a CAD model of our final design. As you can see, we chose a hexacopter with the X configuration. We have our landing gear mounted vertically on opposing legs to increase stability. And our payload is mounted on the bottom frame, centered with the CG. And you can also see an electronic cap on the top to protect our avionics, as well as 2 cameras, one facing the bomb site and one facing forward to pilot.
For manufacturing, we utilize the MAE workshop and senior design labs. That's where most of our time took place in. For the main center frame, we use the CNC water jet to get the desired shape. And then we also use the drill, CNC drill. And we utilize personal 3D printers and NC State 3D printers. And then we, for the arms of the drone, we use a towel saw. And for our manufacturing process, a lot of our components were 3D printed, and that helped with redesigning and retesting within a few days. Like the main center frames were able to be manufactured within a couple of days, and then the tubes for the arms, they were easily cut like within a couple minutes. And then for our electronics manufacturing, the process was soldering and cutting the wires to length.
So the net launcher shoots 4 metal spherical balls out of the chambers into those bags, which drags the net open. The metal balls also help entangle around the target or the animal. The springs are modular, allowing you to pick the length of the springs, which obviously changes the amount of force that the net is launched with. So you can essentially pick the distance at which the net fully opens, which if you want to change your launch height. And then the net is modular as well, allowing you to change the size of your net based on the size of your target.
All right, so the propulsion system, we went through a couple iterations, and you'll see that kind of later in the slides. But we designed around having extremely, being able to pick up our very heavy payload. We are very, very close to that max of 10 pounds that we designed around. So we wanted high torque motors that were able to propel these up and provide the stability as well as the speed and the maneuverability of all of these to get about a thrust to weight ratio of about 2 to 1. Additionally, we had the motor mounts designed around these high G loads that we would experience during flight. So in order to test these and make sure that we were getting the right data, we constructed our own thrust stand to test most of this data. We were able to construct it, and then if you look on the bottom left corner, that is the propellers that we ended up going with.
So with for avionics, we just went with the standard STM32F405 processor or based flight controller for cost. It's responsible for the attitude and positional control. We have an onboard GPS and compass. We went the Spectrum RC protocol. And then we have an onboard Raspberry Pi 4, which is responsible for onboard data processing and also telemetry and video forwarding to the ground station computer. And then we have dual onboard cameras for both I guess aiming the payload and then also FPV style flying. And then we also have a LiDAR rangefinder that provides altitude data and also autonomous landing. For powering the motors, we went with two 33 amp 4-in-1 ESCs running a digital protocol to get RPM data. And then we used power distribution board to power all the different components, and it's powered by a 6S battery.
Yeah, for control, stability and control, we used the RD Pilot firmware, which is what controls the flight controller. It does provide a lot of autonomous control features, which we'll be using as well. We used the pretty standard feed forward PID controls, which we have initial manual tuning, and it has ability to auto tune as well. Just that's another one of the autonomous features. And then on the next slide, we can see the filters that were done on the right, because there's some vibrations that can affect the function of the gyroscopes. You can see some peaks in the graphs on the top right, which we applied notch filters to get rid of, and we applied low pass filter to get rid of the overall high frequency noise that affects the gyroscopes. On the left side, you can see that up to about like 3 hertz or so, our target and actual pitch and roll values match up, so our controller works pretty well and our drone is pretty maneuverable.
For structural analysis and testing, we did a simple simulation on ANSYS Mechanical. This is to simulate the drone while actually in flight and hovering with a 2-to-1 thrust to weight ratio. So we applied a 20 Newton of force at the end of the arms. And this is the stress that we got from the simulation was a lot less than the ultimate stress. So meaning the drone would be fine. And then performing the actual test with the sandbags, the arm was able to hold 65 newtons of force with no deformation. And for the landing gear, with the actual validation testing, it was able to hold 20 pounds of force. This was with the angled landing gear mounts. And performing the drop test with these angled landing gear mounts, it was not able to withstand that impact. So we had to redesign the landing gear to be vertically placed on the arms. And this, in the end, demonstrated a lot more strength, and it was a lot more reliable.
To measure the aerodynamic forces felt by the drone, we used SolidWorks fluid simulation. This created nice visuals, as you can see on the right, with velocity, temperature, and drag. Several iterations were run using this with various angles of attack and speeds to simulate actual real-life situations. And we found the maximum force was much less than the lift and thrust that the drag actually produces. So therefore, the drone was aerodynamically sound. CFD simulations were also run on the battery cover. The 3 metrics we used to determine which cover to use out of the 5 designs we made were which one minimized the most drag, which one regulated the most temperature, and which one provided the most protection to the avionics underneath.
Right, so throughout the design process and manufacturing, we encountered a lot of setbacks, all the way from the beginning where we had delays in getting materials and our limited budget of $1,000, all the way to our first flight test where we crashed because our motors burnt out. However, through these failures, we found that our drone can be easily and cheaply rebuilt since a lot of it's 3D printed, and we were able to improve the performance. Like we changed the motors out, for example, to ones that wouldn't burn out. So.
So now all the stuff you guys care about, the flight testing. So we were able to get it up in the air and actually working and demonstrating that the net worked as well as some of the flight modes. We went through a couple different flight modes, including loitering, so maintaining X, Y, and Z positioning, additionally returning to sender. And then we experimentally tested the drone's net capabilities. We tested it on moving targets and stationary targets, and were able to perform successful captures in multiple different times. Very high speeds also that we were testing, trying to see the maneuverability and the capabilities one of these drones might have. So right here is our drone demonstration, catching a table. not the most interesting of things, but this was the best video we had. So as you can see, it comes down and is able to perform a very low pass to then capture the animal.
So overall, this was a great success for our team. We believe we were able to create and design a fully functioning product and a fully functioning mechanical payload that operated seamlessly with the drone. We were able to achieve high airspeed while also maintaining high levels of maneuverability. And even though we crashed, I think, 4 or 5 times, we were still able to, end of the day, come out with a completely working product that we were very happy with.
So some future capabilities, if we continue developing this, that we want to implement, are autonomous flight and computer vision technology to automatically follow the animals with minimal, or at least assisting the pilot input, AI object avoidance, forward-looking infrared cameras for night flight capabilities. We want stereoscopic depth capabilities to help with, I guess, knowing the target position, and additional applications that we could adapt the system to, or could be larger animals and maybe drone captures.
Thank you.
Thank you.
I see 29 slides there. You have to stop at 25.
They're not rails.
Oh.
And do you have a video that plays?
We do, yeah.
This will be fine, right?
Yeah, can you enable editing? I don't know if that'll. It's this one.
This?
This one.
That should work.
I shouldn't have that one.
Okay, so the last team for today is the LRL Advanced Projects, and the team lead is Luke Nicol. Over to you.
Thank you, Lavia. Okay, good afternoon, everyone. My name is Luke, and let's present first. Yeah, probably critical. Okay, so, Ellie. My name is Luke. I'm part of the Liquid Rocketry Labs Advanced Projects team, and I'd like to present to you our rotating detonation turbine generator. So it's a little different than a drone, but to give kind of a background, who here knows what a rotating detonation engine is? Show of hands. Okay, so half? Yeah, half. So just to give a little bit of a comprehensive background, a turbine system works by bringing air in, heating it up with the flame front, and then pushing it out the back. So this flame front is usually just like a standard flame, like a lighter. However, an emerging technology that has recently been studied is using a detonation wave instead of a flame front. So detonation wave is more thermodynamically efficient, but also a little bit harder to handle. So we plan on using this detonation wave technology in conjunction with a standard turbine system for increased performance as well as less fuel usage, what ends up being more environmentally friendly. So personnel. So from our left to right here, we have Jose, we have Ellie, we have Donovan, we have Rodrigo, we have Corey, and we have Trevor. And they'll go over a little bit about their subsection when we get to them. Organizational structure, Felix Awiri, Professor Felix Awiri, and Dr. James Braun, as well as Lavia, our teaching assistant. I'm Luke Nicol, project manager, and then this is my lovely team. Purpose. We want to create a platform to test different geometries in this detonation wave flow so that we can prove that this technology is both feasible and superior to conventional technology. Standard ConOps, fuel goes into our rotating detonation combustor. It goes into the exhaust, then goes into the turbine, and then that turbine spins to generate power. Functional block diagram, basically what this sums up is we have a lot of sensors on here so that we can get some good measurements as well as make sure that nothing goes wrong during operation. And here is our turbine generator. So we have a scale model that we will be showing at the poster session along with our actual turbine generator. So please come by and you can spin the blades, see how it functions.
Alrighty, I'll be talking about our instrumentation a little bit. You can see in our image here, the exhaust of the RDE enters from the left. Our project is an experiment that is installed in the exhaust of the RDE. You can see that the flow passes over a stator, which conditions the flow before it enters the rotor, which spins up our shaft and produces power through our generator. We need a lot of instrumentation to maintain safety and manage our performance parameters. So we have things like total pressure probes, static pressure probes, a whole lot of thermocouples, as well as a torque sensor and redundant RPM sensors in order to calculate the power the generator creates.
So here is kind of a breakdown of our parts. Rodrigo and Corey will talk a little bit more about them, but each component is machined precisely to fit together with minimal clearance in order to ensure that nothing goes wrong during operations.
Yeah, so I'll quickly introduce the starter generator subsystem. The function of the subsystem is to, at startup, pre-spin the shaft and the rotor up to our operating speeds of 30,000 RPM. And then once the combustor ignites, seamlessly transition into our generator mode, during which the mechanical energy of the rotating assembly is converted into electrical energy. So some of the key elements are the motor, generator, rated to 7,000 watts and 60,000 RPM, as well as our sort of power distribution system consisting of the power supply and 6 regen clamps in parallel, which the function of those is to divert that energy through internal resistors to dissipate it.
So this is our static mechanical portion. This is anything in our assembly that is not rotating, as implied by the name. So its goal is to rigidly fix the position of all our components, especially the rotating ones. So we want to make sure that the stator is properly seated, so is the rotor and the shaft itself, so everything is flowing as we expect. It also houses a lot of the critical instrumentation, as Ellie went over a bit earlier, and it guides the exhaust through, as well as house our sealing system, which we use 200 psi air to make sure no hot exhaust enters where the bearings are at. The rotary mechanical section, everything that's rotating. So the main role of this is to transfer power from the turbine over to the motor and vice versa. So this comprises of a 420 stainless steel shaft. This has a straightness tolerance of 30 micron per 300 millimeters, which is really straight. Shaft length, 130 millimeters. It has 2 millimeter shaft keys to secure the turbine onto the shaft. It contains a miniature bellows coupling, which is balanced to 60K RPM, which is actually twice our operating speed. Angular contact pair, this will hold the shaft axially and also support any loading. Contains an M6 threaded end, so that's to also secure the turbine from, just sort of sliding out in front and rubbing against the stator. Don't want that. And a spacer preload ring mechanism. So a bit of a design process here. That was our original shaft. You might be saying it looks like just like the other one, and all shafts are the same, but I beg to differ. So we tested our equations against some finite element modeling here. We can see that overall we have similar numbers, and so we learned some excuse me, important things. One, our stress values are really low. We're really not concerned about the shaft being stressed. 420 has like a yield stress of around 1 gigapascal, so we're really not worried about that. But we also noticed that our critical shaft velocity was kind of low, so that's where we start seeing vibration, and that is not good. Other things we learned, a stiffer shaft means a higher critical velocity. So using that, we've made some key design changes from that initial shorter shaft. That was around 70 millimeters, also 8 millimeters with, at its largest diameter. So we increased the length for a torque transducer and added those keyways. We made the shaft thicker to sort of bring that up and make up for the increased length of that, adding the torque transducer. We also changed our shaft material. The straightness tolerance is the same. Really, the only thing that was changed is the availability. And we added that spacer ring preload because originally we had a disc spring-loaded preload, but because of that high-pressure air, we had to switch that.
So here's some simple analysis. We began with some simple equations all the way up to finite element analysis. So we began with our simple equations, verified within Simulink, and then used finite element analysis as well as a design of experiments to sort of explore how balanced, where our max imbalance would be to keep our shaft balanced to ISO 1941. And that was around 1.2 milligrams per millimeter of length.
Okay, so the turbine is basically the part that converts the hot exhaust gas into rotational energy for the generator. So for our design, we have a single stage turbine which consists of one stator and one rotor. The purpose of the stator is to redirect the exhaust gas flow into the rotor at the proper angle so we can hit our required power targets. The stator is 3D printed from Inconel 718, and it has a custom camber profile with 15 blades as well. The rotor is the rotating part, which connects directly to the shaft. It is made of 303 stainless, and it uses a NACA 0020 profile with a camber on it, with 15 blades as well. And one thing with the turbine design is we had to account for two flow conditions that are not typically seen in a conventional turbine. The first being the hot exhaust gas flow. The exhaust gas can reach temperatures of up to 2,500 degrees Kelvin, which is 4,000 degrees Fahrenheit, as well as an inflow Mach number of 0.6, which is very high for a conventional turbine as well. So the design and analysis of our rotor started with a 0D isentropic analysis. We used the Euler's turbomachinery equation, which is derived from the first law of thermodynamics, and that was imported into a MATLAB model. And from there, using some inlet properties, we could get the turning angles for our required power targets for the stator and the rotor. And then next, we used a specialized numerical blade generator called Turbo Design, which basically took those inlet conditions as well as some geometric constraints and created a blade profile that would help us reach our power targets. And then after that, we used a specialized CFD or computational fluid dynamics software called ADS CFD. This is specifically made for turbomachinery, and we use that to verify the outlet conditions that we are expected to see from the rotor and stator, and we predicted about a 20% efficiency across the stage. Just to briefly go over some future work, so one of the things we encountered in the CFD is a decently large region of flow separation that you can see at the trailing edge of the blade. That is an efficiency loss and a total pressure loss, so we want to try to reduce that if possible. So some of our future design considerations include a longer blade to help keep the flow attached onto the surface, as well as taking into consideration the structural implications of doing a design like that as well.
I'll be quickly going over the manufacturing of all the parts. Static mechanical started about 55 pounds of stainless steel stock, whittled it down to about 9 pounds. With the amount of material I had to remove and the precision required for every single part, I was very familiar with sunrises at EB3. We used micrometers, bore gauges, and calipers to get all these parts in spec. Once I made the part, I put on surface plate to make sure the opposing faces were in parallel spec to make sure I don't have an angular tolerance stack up across the whole assembly. A couple basic CNC mill operations, thread milling and 3D contour milling, and some instrumentation milling. Rotary mechanical was all lathe work mostly. Again, 420 stainless steel shaft, turned down the lathe to a couple micron tolerance, and then just some basic thread milling and keyway milling on the end of the shaft. The rotor's being manufactured by Kamal at Fitzwillard. Full 4-axis milling, it's 303 again. And then again, the stator was printed out of Inconel, so the only thing I had to do on that is thread mill it to accept the center body.
All right, I'm going to go over our risk management techniques really quickly. We follow the hierarchy of controls, which goes in order of eliminating a hazard, substituting it for something less risky, using engineering and administrative controls. We do need the hazards of high temperatures and high rotational speeds to be present in order to test. So most of our risk management comes down to engineering and administrative controls. Some examples of those are including safety factors. When we engineer our structural components, we have a go, no-go system where before every single test begins, every instrumentation must be sending a signal back to the control system. We also have administrative controls, such as we use a very short test time, which means we don't need active cooling, and there's just not much time for anything to go wrong. We've done extensive modeling throughout our design process to make sure things are acting as we expect. We've also done a verification, validation, and testing process on our physical components. Some examples of those tests are listed here. We've done things like check that our stator and rotor will actually spin when we introduce them to an airflow. We've done some instrumentation checks of our pressure transducers, thermocouples, torque transducer. We've done many tests of the RPM capabilities of our motor, making sure that our pre-spinning function will work, as well as sensor tests of the motor controller and the torque transducer. I'll hand it over to Donovan to go over the next test.
Yeah, so what you're about to see in this video is a test of our starter generator system integrated with the actual mechanical assembly. So using the software for our motor controller called VESE tool, we commanded it to 35,000 RPM. We actually enter 70,000 ERPM, but that's just because our motor has 2 pole pairs. And so we validated our speeds in the software, as well as using a spectrum analyzer on a smartphone. Yeah, so as you can see there, we measured a dominant frequency of 586 hertz, which aligns with the speed that we commanded of 35,000 RPM. A very small disagreement there. If it sounded not as smooth as you would expect, that's because we our coupling, which is a miniature bellows coupling, did not arrive in time. So we're using an alternative coupling there.
And finally, I'd like to extend a special thanks to everyone who's helped with this project. So here are a few of the companies that provided software, materials to help us make this project real, as well as the NC State MAE department who provided this course and funding and everything like that, as well as Dr. James Braun, who was an excellent source of inspiration and a guide during this project. Finally, I'd like to reiterate that if you have any questions, please stop by our poster. We have both a full-scale model and the actual turbine to play around with. Thank you.
Remember when you went to the
Yeah, I remember when I went to the end. That was actually so fun.
All right, folks, let's head on over to EB3.